Hello everyone! I welcome you all to the amazing platform of Physics Wallah English Wallah channel. Today, I'm Harsha Soni. I'm going to teach you a very new chapter, one short lecture of our chapter Classification of the Elements and Periodicity in the Properties. We have to study the one short lecture required for your examinations, JEE, NEET, board, anywhere you want to study. So, before starting this chapter, I want to just ask you one question. Let's say you enter in your room. There are pants everywhere, there are shirts everywhere, there are t-shirts everywhere. Okay, you want to wear certain kind of a t-shirt, certain pant, but you're not able to find them. So what you will do? You will just open your almirah. You will place all of the pants in one column, all of the shirts in one column, all of the t-shirts in the one column. So you are able to identify which of the pant you want to wear, which of the shirt you want to wear. Same is the thing with our periodic table, right? We have so many elements present with us. We were having so many elements present with us at that particular point of a time. But we were not able to study them efficiently. We were not able to study that which element should be placed together, which should be placed far, what should be the property in which they should be placed so that we can have an efficient way of study. So for that only, we have to start our chapter, Classification of Elements. So let's start the chapter. First of all, whenever we are starting a chapter or whenever we are making a periodic table, a certain perfect periodic table, there are many scientists. They will come, they will say some sort of a things. Some of the things will be accepted, some of the things will be rejected. So accepted things are, accomplished and then they are put into a particular manner that will give us the modern periodic table. But before that, there are many scientists that have said many things. So we have to study all of them. It's okay, many of the points were rejected, but for the examination point of view, we have to study all of them. So first scientist, according to our syllabus, the first scientist, the work of that respective scientist is Daubernier-Trides. What is the basis? First of all, we have to know the basis. Basis is increasing atomic mass. Okay, what he did? He took a triad in which 3 elements are present. Fine. There you can see in all of them there is a triad. Triad means that there is a set in which 3 elements are present. What he said was, if we take the average of first element and the last element, if we take the mass average of the first element and the last element, that will be exactly equal to the middle one. That was the basis of the selection of the Daubernier-Trides, right? Let's say if I take the example of lithium, sodium and the potassium. So lithium, then we have sodium and then we have potassium, right? So lithium is having its atomic mass as 6. Potassium is having its atomic mass as 40. So if I take the average, 40 plus 6 divided by 2, it is coming out to be 23. And we all know that very nicely that the atomic mass of the sodium is 23. So we can say that if the first element and the last element, if we take the sum of their atomic mass, we divide it by 2, the number which is coming out to be will be exactly the atomic mass of the second one. That was the basis of the selection of the Daubernier-Trides. It is followed by every of the element present over here. It can be asked that in the question, in the examination, that which of the following follow the Daubernier-Trides. There are some of the cases which are present over here, and let's say if I replace bromine with the iodine, that will not follow triad. If I replace, let's say, selenium with oxygen, that will not follow the triads. One more thing I should tell you is, first is the method through which you can calculate, right? One of the other method is also present, that is also very easy. Let's say lithium is present, let's say sodium is present, and let's say potassium is present. Let's say if I write the atomic number of these elements. So what is the atomic number of lithium? That will be 3. What is the atomic number of sodium? That will be 11. And what is the atomic number of potassium? That is the 19. It is easy to remember the atomic number as compared to the atomic masses. So what you can do is just have the difference of these two. 11 minus 3, the difference will be what? 8. Just have a difference over here also. Same, the difference will be 8. You know, if you get the same differences, then also it will follow the Daubernier triads. So these are the examples. Just remember the example. Just remember these two methods, how you can calculate or how you can identify. That's it. Daubernier triads is done. Let's move towards the next model. So we have the Newland's law of octave. You know, we have heard Saregama. Here also we have to do the Saregama. First of all, we should have the basis. What was the basis? Basis was also the same, increasing atomic mass. But there is a property associated with this Newland's law of octaves. What was the property? Every eighth element has properties similar to the first element, and this is valid from lithium to calcium. Okay, this is valid from only lithium to calcium. This was the basis of the selection of the Newland's law of octaves. Now see the same in the form of the table. You know that there is a musical note, sa re ga ma pa, right? So let's say I start with the hydrogen. Okay, so sa re ga ma pa dha ni sa. When again this word sa will be repeated, the element will be present. Okay, again you start with the fluorine, the element will be coming out to be chlorine. So when you put all these elements in according to the musical notes, that every eighth element will be having the properties similar to the first element, right? You have to remember this thing. Similarly, you start with the lithium, 1, 2, 3, 4, 5, 6, 7, 8. You are reaching towards sodium, similar properties. Start with the magnesium, 1, 2, 3, 4, 5, 6, 7, 8. Calcium is having the same property as the magnesium. So only one thing you need to remember is this respective basis of selection, that every eighth element is having properties similar to the first element. And yes, this respective model was only followed till calcium. After that, this was not followed. So you have to remember this thing also, that this is only valid. This is only valid till calcium. Although we can write for the other ones also, but we have to write this point over here, that this is valid only till calcium. So do not forget this. Okay, so let's move towards the next model. Even I have written a other table also for you. You can refer any of the table which you find the easier one. Newland's law of octaves, right? Next we are having a graph, which is a Lothar-Meyer graph. It is very important for the examination point of view and very easy also. What he did, what was the work of Lothar-Meyer? See, basis, physical properties such as atomic volume, melting point, boiling point is used, and the graph between atomic volume and the atomic mass was created. You can see the graph also. This is atomic volume present, this is atomic weight present. You will get a certain kind of a graph, and I will tell you what is the important points regarding this graph, and this graph is very, very important, right? So let's study. First of all, there's a point written over here, which is strongly electropositive elements are present on the peaks. You know, there are electropositive elements which are group 1 also, which is group 2 also, alkali metals also, alkaline earth metals also, but they have mentioned over here that they are talking about the strongly electropositive elements. So surely they are talking about the alkali metals. So they are present on the peaks. Just mark them. So whatever is present on the peak, we will mark them with the red color, which is the very strongly electropositive element. What the next they are saying, all noble gases are on the ascending position. We will discuss this in just a certain time. Alkaline earth metals on the descending portion. Alkaline earth metals are also electropositive. They are on the descending portion. You can see which one I am making with the green color. These all are alkaline earth metal. You can see one which is in the descending position. See, this is the ascending, so this is the descending. Okay, when you're moving from the top to the bottom, this is the descending position. So whatever is marked with the green color is the descending position, right? After that we are having electronegative elements on the ascending position. Electronegative elements, you know that where the electronegative elements are present, so we have to mark them also. These are all your electronegative elements. These are present on the ascending position. You can see in all of them, all of these are present in the ascending position. Next, what we are having? Next we have over here is bottom has the transition elements, and even the metalloids are also present. Like if I say these elements which are present over here, these elements which are present over here, you can write over here that these are your metalloids. These are your metalloids, or you can say simply these are transition elements. You can call them as metalloids or you can call them as transition elements. So it is very important to understand that where all the elements are present. I have not written the noble gases over here. If you want to write, you can write the noble gases also. See, what they are saying is all noble gases are on the ascending position. So you have to mark them on the ascending position. But here there is a fluorine present, here there is a sodium present. So where will be the noble gas? Obviously, it will be present in the between. It will be present in the between. I can also have a mark on this noble gases. So it is very, very important to understand where exactly the elements which are present on the peaks, ascending position, descending position, the bottom lines. You have to remember each thing, because this graph, I'm making a star over here. This graph is very, very important. I have marked each and everything. Okay, so let's move forward. After that, we are having the atomic volume was chosen as the basis of the periodic classification of elements by. There's a question which is a previous year question which has been asked. I have not written the year, but this is the previous. Every question present in the class today will be the previous year question, and if you are able to solve them, you will have a very good confidence, right? So you know that atomic volume was the basis of selection for whom? Right now we have discussed Lothar-Meyer. Atomic volume graph with respect to the atomic mass what was made by Lothar-Meyer. Done. We have done this question. Next question we are having. In the Lothar-Meyer graph, there are some points written A, B, C, D, E. So you know very well what are these points, where exactly, what exactly is present on the peaks. Should I tell you, or you know them? What exactly is present? Strongly electropositive elements which are alkali metals. So alkali metals are present on the peaks. You know that alkali metals are present on the peaks, so you can answer this question very easily. I have already told you that the graphical questions with the Lothar-Meyer graph is asked, right? So let's move forward. Next. Okay, so this person is having a very vital role in the classification of elements, in the making of the periodic table. Like, he has done a very good job. 90% of the making of the periodic table is done by this respective person, which is the Mendeleev. And we have to study his periodic table, Mendeleev's periodic table. Every point in this table is important. So let's start. Basis. Same is the basis. What was the basis? What was the law? That the elements are placed according to the increasing order of their atomic masses, right? Basis was this only. When the Mendeleev was studying, was making the periodic table, only 63 elements were known. Only 63 elements were known, okay? Increasing atomic mass, I'm just having an underline. You have to just remember the key points, what I'm having as an underlined or the circle one. Just remember the key points, right? So only 63 elements were known. The basis was the increasing atomic mass. See, when Mendeleev came, now there was no, the noble gases were not discovered. But when he was working, then only it was discovered in the middle of his working. So we have a modified form of the Mendeleev's periodic table, in which there is a separate group of the noble gases that is called as a zero group. So in the first table of him, there was no separate column, there was no indication of the noble gases, but in the modified form it is present, right? So no inert gases were discovered initially, but in the modified form were discovered. Okay, we will discuss about this point number 4 in some time. First, we should discuss about the Mendeleev's periodic table over here. You can see here the beautiful table discovered or made by Mendeleev. So, first of all, we have over here 7 periods. You can see very nicely over here There are 7 periods present in the Mendeleev's periodic table. Groups. Now what are the number of groups present? 1, 2, 3, 4, 5, 6, 7, 8 and the 0 group. So these are the number of groups present in the Mendeleev's periodic table. If you see nicely that if you have a group over here, this group is divided into two parts, which is one is A and other is B. The groups are divided into the two parts. Let's say if I have this group number 1, it is divided into two parts. One of them is A and other is B. You can see this in the every of the group which is present. If you talk about the periods, even the periods are also divided into the two columns, right? Let's say if I have a fourth period, it is having a first series, it is having a second series. है ना? Same is with the fourth, with the fifth one and the sixth one. Fourth, fifth, sixth, all the three have the same category that their periods are also classified into the two series. Groups are always classified into the two respective subgroups. I can say that will be the A1 and the B1, and the periods will be classified as the first series and the second series. Done? So you can have your whole of the first series present over here, whole of the second series present over here. See, the block is same. There is no difference of the blocks. Blocks is same, but the series are different. So we don't have to learn the Mendeleev's periodic table. You should remember this thing. We don't have to learn this table, but we should understand this table. Like what kind of a questions can come. They can ask you number of periods. They can ask you number of groups. Is there any subgroup? Is there any series present in the periods? If there is series present, so in which period the series is present. Like I have no series in the first, second or third or the seventh one. I only have in the fourth, fifth and sixth. So understand the key points of the Mendeleev's periodic table, right? So this is the thing. And in the zero group, you can easily see, in the zero group, there are noble gases. In the zero group, you can easily see that there is a noble gas present over here. There is a noble gas present in the respective zero group. Now, understand that what are the limitations of this respective periodic table. Now understand. You can see over here, there is a periods present, there is a columns which is group present. You can relate rows with the periods, you can relate columns with the groups. So we have already done this. 7 horizontal rows, 8 vertical columns. Columns will be called as groups, rows will be called as the periods. Done. Don't get confused with this. Might be a question can be there that they will replace the periods with the rows. You don't have to get confused, right? Let's move forward. So first of all, we have to discuss about the vacant spaces. Let's first discuss the point number 4. You know, what was the best thing about the Mendeleev's periodic table was that he has left some spaces. He has left some spaces, like if I say aluminium, there was a space left, below aluminium that was called as Eka aluminium. He just left some empty space over here, down of the aluminium, and it called as Eka aluminium. He was knowing that there might be in the future element will be discovered and it will be present over here only. Hai na? That is a very new thing, very good thing. Mendeleev was the basis of selection of this, right? So he left the space below the aluminium and it was Eka aluminium. Later it was called as the gallium. After that, silicon. Below silicon also he has left some space. That was later called as germanium. Mendeleev named this space as Eka silicon. After that, what he did? He did for the boron also. He left the spaces for the boron, he left the spaces for the manganese, and I will teach you. See, what he did was, if I have aluminium over here, right? If I have aluminium over here, he left the space below aluminium. Silicon, he left the space below silicon. Boron, left the space below boron and left the space below manganese, and he named them all of these as Eka aluminium. He named these as Eka aluminium, this as Eka silicon, this as Eka boron, and this as Eka manganese. And Surprisingly, yes, elements were discovered, were placed in these respective columns. This was called as gallium, this was called as germanium, this was called as scandium, and this was called as technetium. So all these elements were discovered according to the Mendeleev. What he said was totally correct. You just have to remember the examples. Mendeleevs have done this work, right? After that, what we are having is the drawback. See, the basis of the selection of the Mendeleev periodic table is according to the atomic masses. Let's say if I talk about the isotope, let's say if I talk about the drawbacks of the first point, I have carbon, and carbon is having two isotope. I have 12 also and I have 14 also. It's okay, I have placed this carbon over here, which is having the atomic mass as 12. What about the carbon 14? Where I should place this carbon 14 isotope? I don't have any place for the isotope. So this was the limitation of the Mendeleev's periodic table. After that, obviously, you know that this hydrogen is always having a problem. Right now also we don't have a particular space for the hydrogen. So there was no position of hydrogen at that time also. And right now also we are facing this problem. So this was also the limitation. Anomalous, you know, there were some anomalous pairs. What he was saying that I have arranged the elements in the increasing order of the atomic masses. So why you have these kinds of problems? Argon is having 40 as the atomic mass. Potassium is having the 39. So why they are placed in such a manner? See, if I tell you about the argon, see, argon having 39, I should change the color. Argon is having 39.948. Argon 39.948 as the atomic mass. And if I talk about the potassium, atomic number is 19, but the atomic mass is 39.102. This is not acceptable, right? We have the increasing atomic mass order. This is bigger in the number, this is smaller in the number. So this is an anomaly of the pair, right? After that, there was so many other anomaly also. You can see in the case of the cobalt and the nickel also. See, in the case of the cobalt and nickel, this is 58.9, this is 58.7. You can see the anomaly over here also for the cobalt and the nickel. And one more was present, that was your respective tellurium and iodine. Tellurium being 127.6 and iodine being 124.9. So this is also incorrect. This is also an anomalous pair. So beta, you need to remember these all pairs very nicely. I am not telling you to remember every of the thing of the Mendeleev's periodic table, but just remember what I have told you. You have to remember about the spaces which was present and what were the anomalous pairs which were present, so that you can answer efficiently, right? You can locate them. You know, you should do one homework. You should, in your NCERT or any of the place where the Mendeleev's periodic table is available to you, just locate all these anomalous pairs. Okay, you will have a greater understanding of the Mendeleev's periodic table, right? Let's move forward. After that, one more thing I should tell you is, you know, beryllium. There's a problem with the beryllium also. Beryllium was considered as having the valency as +3. It was considered that beryllium is having valency +3, and if I talk about the equivalent weight of beryllium, that was 4.5. So if I calculate the mass of the beryllium, you know, according to the mole concept, if I calculate the mass, it is coming out to be 4.5 into 3, which is 13.5. So according to them, if beryllium is having the valency as +3, it is having the mass as 13.5. So this is carbon and this is nitrogen. So I should place beryllium in between these two. So this is 12.01, this is 14.007. I should place this beryllium somehow in between these two elements. This is not acceptable. This is not correct. So this selection of beryllium as +3 valency was incorrect. Exactly what should be the correct answer? Beryllium is having the +2 valency, right? So if you calculate the mass according to the +2 valency, coming out to be 4.5 into 2, which is 9, that is totally correct and can be correctly placed. So this is also a limitation. If I write, I will write as a fourth point, this was also the limitation, this was also the limitation, and you should know this. Okay, this was also the limitation, that some of the elements were not having the correct atomic masses according to the Mendeleev. So we have corrected them, right? So I will write the cases: uranium, beryllium, even gold, even platinum. All these elements, atomic mass was corrected. Atomic mass was corrected. So remember these elements very nice. You need to remember only, I have explained the beryllium, you can remember the rest ones. Okay, let's move. This will not be asked in the NEET, but JEE it can be asked. Examination point of view, NEET is not important, but JEE is important, right? The NEET ones can leave this, the NEET ones can leave this. Let's move forward, ma'am. You have explained so much, right? Okay. After that, okay, everything is fine. Everything is going good. But Mendeleev is not happy because, you know, some of the people are poking him because of the limitations present. Why in Mendeleev you are having these anomalous pairs present? What is the problem? Just correct it. And Mendeleev is very upset. So there is a person now, mostly. He is seeing Mendeleev that he's sad. He's not, encouraged. He's not motivated for what amount of a good work he has done. So what he did was, he did experiment. What experiment did he done? He just made a graph. What graph did he made? He made the graph between, see, the graph is very, very deep. I'm just telling you the very key points of the graph, right? This is root of frequency and the atomic number graph. What he did was, he first made a graph of this root of frequency with the atomic mass, है ना? And after that, what he did was this under root of frequency and the atomic number. In this case, the graph he was getting, was very zigzag. But in this case, the graph he was getting was exactly the linear graph. This graph was considered as a linear graph. At that particular time, this respective point of the linear graph clicked into his mind, and he just called Mendeleev and said, see, brother, whatever work you have done is very good. You have just done 90% of the work. Just make a little difference. Just change your basis. The increasing atomic mass is incorrect. Just change that into the increasing atomic number, and all of the anomalies will be vanished. And Mendeleev just listened him and changed this, and we got the new periodic table. But that was not the work of the Mendeleevs. Now we have Bohr, Bury, Warren, so many scientists, 4 other scientists were also present, that were the basis of the classification of the modern periodic table. But yes, Moseley was the person who did this experiment, that we should not consider the basis of the increasing atomic mass, but as the increasing atomic number. But you know that this line was given by Moseley, but then some other works are done, some other scientists say some other things, they do the experiments, and the final periodic table was given by Bohr, Bury, and some 4 other scientists were also present. Warren was also there. So Mendeleev has done his work. There is very good work done by the Mendeleevs, but there is one problem: increasing atomic mass. So there were anomalies present. Moser did the experiment. Root of frequency calculated with what? Atomic number. Graph came out to be linear, and he told all these things to the scientist. Now the 4 scientists, Bohr, Bury, Warren, and some 4 others were also present. They discovered the periodic table, and they gave the modern periodic law, which is the physical and the chemical properties of the elements are the periodic function of the atomic numbers. It is not the atomic mass which should be taken as a basis of selection. Increasing atomic number. Here all the things have been changed. Now there is no problem. Isotopes, we are not taking the atomic masses, so why isotopes will be considered, right? So position of isotopes were discovered. They were not included in the periodic table because we are taking the atomic numbers. And position of anomalous pairs already corrected. Koi problem? There was no problem, right? Let's have a water break. Just 1 minute. you should remember the Moseley experiment. So position of isotopes is done. Anomalous pairs are already auto-corrected, right? Perfect. Now, according to the Moseley, a straight line graph is obtained on plotting the frequencies. Word is incorrect. We don't have a frequency. We don't have the square of the frequencies. We have the square root of the frequencies. First word is correct now, right? The square root of the frequencies of characteristics X-rays of the elements against their atomic numbers. So C will be the answer as you have discussed. Now, we have to discuss now some important key points of the modern periodic table. First of all, the modern periodic law that the elements are arranged in the increasing order of the atomic numbers. Now, what other, classification of the periodic table we have to understand, right? There are 7 periods. There are 18 vertical columns called as groups. Each period corresponds to the highest principal quantum number n of the elements in the period. First period contains 2 elements. Subsequent period consists of 8, 8, 18, 18, 32, 32 number of elements. 18th group is considered as the noble gas. See, these 2 points we have to discuss. Rest of them you already know. We know all these things. We will discuss these 2 points right now only. And these numbers are called as the magic numbers, which tells us the number of elements in a period. They tells us about the number of elements in the period, right? So let's move. 14 elements of both 6th and 7th periods are placed in separate panels. Lanthanides and actinides are the names of these panels, and elements with similar electronic configurations are arranged in a vertical column called as groups, right? So let's first have a look on our periodic table, what exactly we have to study in these respective groups, columns and everything. This is the modern periodic table present in front of us. These 2, the very left groups are called as the S block elements. These left hand side groups will be called as the S block elements, right? The very right hand side of the 6 groups will be called as P block elements. The 6 groups present over here is called as P block elements, and the groups which are present in between from the 3rd to 12th are called as D block elements. So I am first writing over here. This is first group. This is second group. Combinedly they are called as S block. This third group to respective 12th group is called as D block elements. This respective 13th group to respective 18th group, this 13 to 18 will be called as P block. First of all, we should know that where the elements are present, where exactly is the S block, where exactly is the P block, and where exactly is the D block. Now what or where does the S block, not F block elements are present, right? So we have lanthanum over here, we have actinium over here, and I am writing over here this respective circle. So this circle corresponds to lanthanide and this circle corresponds to actinides, which are present not in the D block elements, but exactly the position of these elements are inside the D block elements only. See, there is a group number 3 in which lanthanoids is present and actinoids is present, but the lanthanoids are present in the period number 6, whereas the actinoids is present in the period number 7. These all are your period numbers: 1st, 2nd, 3rd, 4th, 5th, 6th and the 7th. Lanthanoids are present after lanthanum. Actinoids are present after actinium. You can see very nicely over here, right? Lanthanoids are all these elements which are present with a yellow fluorescent color. Actinoids are the elements which are present below these. 14 are the lanthanides and 14 are the actinides. They are present in the group number 3, lanthanides in the period number 6, actinides in the period number 7. I'm writing this over here. I'm writing this. Lanthanide is present in the group number 3. They are present in the group number 3. And period number 6, they are present in the group number 3. And they are present in the period number 7. Do not forget this. This is very important with respect to the examination point of view. So S block, D block and the P block, then we have the F block. If I write the order in which they are present, to the very left there are S block elements. After that what? First you have what? F block elements. After the S block elements you are having the F block elements. After that you are having the whole this D block elements, and after that you are having the, in the very right hand side, the P block elements. You should know this, that they are arranged in the form of this order. First of all we have SFDP. SFDP, do not forget this. We have from left to right SFDP. First of all, the very left hand side is having S, then you can see very nicely there is F, then D, and then there is P. Right? Okay. There are many things we have to discuss, but we are just moving towards the key points, right? Okay. You know, the very left hand side elements are considered as metals. Metals. The in between elements, the S and P block are present. In between them, some elements are present which will be called as the transition elements. To the very right hand side, there is a mixture of non-metals also and metals also and the metalloids also. Okay, there are some elements with the green marked, they are considered as the metalloids. Some of them which is present over here is considered as metals, and above that this blue colored one and the yellow colored one are considered as the non-metals, right? These red and yellow are considered as the metal, the green one is considered as metalloids, and blue and yellow, all of these are the non-metals, right? We will be having the written ones also, but I'm telling you all these things in the periodic table itself, right? Okay. After that, let's move forward. See, when you have understood that these all respective elements are present, there are some blocks which are present in the periodic table which are empty, and they will be given some name also. But you know, in the very before time, there was no specific name. So we were having some rules in which we have to write the names of the elements. Let's say, if I want to write a name of the element which is 101, let's say 106, let's say 113. So what should I do? I am having a certain rules. I have to follow those rules and I will get a particular name. Let's say, first of all, we have some names of the numbers. 0, 1, 2, 3 till 8 we are having. Okay. 0, nil, un, bi, tri, quad, pent, hex, sept, n. Right? We are having this 8 as oct, and for the 9 we have n. Okay. Just remember this thing very nicely. Now let's say I have to name this element 101. So for the 1 I will write un. For the 0 I will write nil. For the again 1 I will write un. First you have to do un, nil, un. Un, nil, un. And the ending ends with the word em. Un, nil, un, em. Okay. So un, nil, un, em. You always have to end your name with the em word. Okay. First of all, un for the 1, nil for the 0, un for the again 1, and then em with the ending. Okay. Un, nil, unium. Now you have 2 at the ending. Un, nil, bium. Un, nil, trium. Un, nil, quadium. Un, nil, pentium. Hexium. Septium. Octium. Ennium. In this way you have to follow. Right? But you know, we need to remember the symbols also. So if you have a un, you write u. First letter will always be the capital one. Then you have nil. So nil starts with the n. So write n as a symbol. Then again you are having the 1. So write u as a symbol. So u and u will be the un, nil, unium. Let's say I have 108. So 1 is the un. So you will write over here the u. Then 0 will be the nil, right? N over here. And there is 8. 8 is having octium. Oct. So O. So we will write the UNO. Okay. So these are the symbols. These are the names. These are the numbers. And these are the names of the numbers you need to remember so that you will be able to write the names. After that, there are some specific names. Now we have the total names of all the elements, total 118, like 118. All the elements have their own names. First, we were not having these names, so we were having the certain rules in which we can define the names. But now we have all of the names, which some of them are on the basis of the scientists, some of the basis of the properties. There are certain bases on which the names have been decided. So you need to remember all of the things, each and everything. You know, a question came in NEET 2020 only from this table. So you can simply understand the importance of this table. Every of the respective block over here is very, very important, right? So let's move forward. Yes, there is a question came on this also. Which all elements are discovered in the 2016? You need to remember this also. This is also very, very important. That nihonium, moscovium, tennyson, oganesson, you have to remember all of these were discovered in 2016. Okay, there's a trick also. Na maro tum aur. There's a trick also. Na maro tum aur. This is a Hindi trick. You can just remember over here. Na maro tum aur. That means that don't beat us more. So na maro tum aur. Don't beat us more. I'm telling you this trick in the English. Okay. This is a trick. If you can remember these names normally also, you can remember normally. But you have to remember this because this is important. So we know that all of the elements which are discovered in 2016. This question has been came in the respective examination of the JEE. So let's move forward. Before moving forward, I want to explain you one of the point which was present over here. See, first period contains 2 elements. After that, subsequent period consists of these number of elements. So how do you get to know that these respective elements are present? That will be discovered when you are knowing the electronic configuration of S, P, D and F block elements. And after that, we were having this respective point 14 elements, the lanthanides, 14 elements, the actinides, where exactly they are present in the periodic table. You should know that, right? Okay. After that, next we are having over here is a question. Identify the incorrect match. Name, aniline. So what is the name of the aniline? You can see from the table and you can answer. Aniline. What is the number associated with aniline? Aniline. This is aniltrium. This is anilhexium. This is anium. Okay. So 101, very true, which is Mendeleevium. That is correct. Aniltrium, Laurentium. That is also correct. Anilhexium, that is Seaborgium. That is also correct. But anium is not correct. That is not the Darmstadtium. If you want to see, you can see from the table on also. I have a table over here. We have 101 as your Mendeleevium, that is correct. We were having 103 Laurentium, that is also correct. The incorrect was 111. They were calling them as Darmstadtium, but that is not Darmstadtium, that is Roentgenium, right? 111 Roentgenium is the correct answer. They were calling Darmstadtium, which is not 111, that is 110, right? So this is the table through which you can answer the question. So this is not the Darmstadtium, beta. That is, Darmstadtium is in the 110. So this is incorrect option. Identify the incorrect option, which is the only one, which is the D option, which is the fourth one. And this is the question which has come in the NEET 2020. So you can understand the importance of that respective table. Let's move forward. Now see, you know that where exactly S block elements are present. You know where exactly P block, where is D block, where is the F block. So we have to now understand every of the respective elements like S, P, D and F, why they are called as S block, what is the general electronic configuration, what all elements are present and what are the usual properties, right? So first of all, we are having the S block elements. S block elements are having their group number first and the group number second. First is having the element as lithium, sodium, potassium, rubidium, cesium and the francium. Francium is a radioactive element, so we don't have the studies of these elements, the radioactive elements. We are not having the exact properties, so we just ignore them with respect to the study, right? Second respective group, which is beryllium, magnesium, calcium, strontium, barium and radium. Radium is, again, it's a radioactive element. So you need to understand or remember the properties of all these elements which are coming under the S block element. The first group is called as alkali metals. This respective is called as first group, which is the alkali metals having the general electronic configuration as NS1. Group 2, which is the alkaline earth metals, is having the general electronic configuration as NS2. If you want to write the general electronic configuration of the S block elements, that will be considered as NS1 to 2, NS1 being alkali metals, NS2 being alkaline earth metals, right? After that, we have the electron enters S subshell. Why do we call them as S block elements? You know, the definition of any of the block elements is whenever you enter, your last electron enters the S subshell, you are a S block element. If it enters in the D subshell, you are a D block element, right? So the definition is done. After that, all of these elements are metals. You consider any of these elements, all of them are metals. All of them are metals, right? After that, they have a very low ionization energy. I don't know if you're knowing the ionization energy right now. You know already because you are about to give the examination, so you know all these things. They have a very low ionization energies because they are present on the very left hand side of the periodic table. So they have a bigger sizes. So if you have a bigger size, electron removal is very easy. You have to just supply very less amount of the energy to release that electron. So they have a very low ionization energy. That's why they can release the electron and they can be very highly reactive. If you have the ability to donate the electron, to release the electron, you are highly electropositive. So all of these points, all of these properties are associated with the S block elements. And understand one thing also, beryllium sometimes, I'm writing over here, beryllium sometimes is not considered as alkaline earth metal because it forms amphoteric oxide. See, there is a point related to the metals that they form the basic oxides, but beryllium is having a problem that it is not forming any kind of a basic oxide, it forms the amphoteric oxide. So it is not considered as in some of the cases you will find, in some of the questions, you will find that name an element which is not considered the alkaline earth metal but present in the group 2. So answer will be beryllium. And what is the reason? They might ask you a reason, specific reason. This is the reason. All of them form basic oxides. Metals, they all are metals. So they will form the basic oxides. There is no exception to that. But beryllium is having a problem. It does not form any kind of a basic oxide. So these are the important points related to the S block elements. After that, P block elements. P block is a very big number of elements groups and present between 13 to the 18. Remember beta, very nicely remember 13 to 18, right? After that, general electronic configuration NS2 NP6, right? General electronic configuration is NS2 NP6. It starts with the P1 and end with the P6, right? So if you have your group number 15, I should not start with the 15. I should start with the group number 13. 13, 14, 15, 16, 17 and the 18. So NS2 is common to all. Here they are having NP1, here they are having NP2, then we have NP3, then we have NP4, then we have NP5 and then Here is a complete NP6, which is the noble gases, So this is the electronic configuration of all the groups present. After that, last electron enters the p subshell. You can find this very easily. Let's say I have an element. Nitrogen. Let's say I have an element nitrogen having the Z as atomic number being 7. So 1s2, 2s2, 2p3. Where exactly is the last electron entering? It is entering in the p subshell. So why I will call it as any other? I have to call it as the p block element, right? The definition is this. After that, here electron is filled in the outermost shell. Now what it means? Now understand. Whenever we write electronic configuration as ns2, np, 1 to 6, here n is given the name as outermost shell. Here n is given the name as outermost shell. So we are entering the electron in the outermost shell. There are some electrons present in the inner shell. When you are filling the electron in the p respective subshell, you are entering that into the outermost shell. So n represents the outermost shell, right? After that, there are some specific names of each of the groups, right? There is group number 12 also, there is group number group number 13 also, group number 14 also, but they are not having any specific names. Group 13 can be called as most heterogeneous family. I can write group number 13 also. I can write over here that group number 13 is also present. So we called it as a most heterogeneous family. This group number 13 is called as a most heterogeneous family. Now why do we call it as most heterogeneous family? Because it has exceptions. It has high number of exceptions. Exceptional trends. There are so exceptional trends present in the group 13 family elements. So we call them as the most heterogeneous family, right? Group 15. Group 15 will be called as some name which is very different. We call it as nicogens. Nicogens. Most of the compounds formed from the elements of this respective group are carcinogenic, very poisonous. It's not good to inhale them. So all these words are associated with the nicogens. After that we have group number 15. After that we have group number 16. Group 16 is the oxygen family also. It is called as the oxygen family also, and chalcogens also. You know that when you study the chapter metallurgy, there are certain number of ores which are oxide ores, sulfide ores. So they are combinedly called as the chalcogens, right? After that we have group 17, which is the halogens. Most of the salts of the respective group number 17 are found in the sea. So it is called as the halogens. After that, group 18. Group 18 is called as the noble gases. Noble gases, inert gases. The correct word is noble gas, you know. We should not call them always as inert gases. What is the reason? Because some of the gases which are not present in the 18th group are sometimes called as inert gases, because inert in itself is a word which explains that it does not want to react at a particular condition. There might be a situation that you change the temperature or you change some other condition and that respective element or a gas becomes reactive, right? So noble is the correct word we should use for the group 18 as compared to the inert, right? Like example N2, the dinitrogen gas, the N2 gas, the dinitrogen gas is also considered as inert at room temperature. But when you increase the temperature, it becomes reactive. So at room temperature, it is an inert gas which does not want to react because of the very high bond dissociation enthalpy of the NN triple bond, right? After that we have that group, these p block elements are called as representative elements. Now what do you understand by this word representative elements? What is representative elements? Now understand. See, what happens is, you know, most of the compounds which are present around us are made of some some elements. The elements which form maximum number of compounds are the S block elements and the P block elements. They represent the chemistry of the most of the compounds. Most of the compounds are formed from the S and P block elements. They represent the compounds. So S and P combinedly called as representative elements. Even the S block and the P block both are called as the representative elements. But you know that if I ask you, is there any compound possible for the group 18? Your answer will be right now, there is no compound. But yes, there are some compounds formed for the group 18 elements also, like xenon, and some for the radon also. But right now there are no much compounds of the group 18 also, so they don't represent the chemistries of most of the compounds, right? So S and P block is combinedly called as the representative elements, but group 18 not, because very less number of compounds are formed. Very less number of compounds are formed from group 18 elements. S and P block combinedly is called as the representative elements, right? After that, even the representative elements also, and even you can call them as representative word, is also having a synonym, which is main group element, right? Mixture of a metals, there are certain number of metals, non-metals and the metalloids. These all elements are only the metalloids. Silicon is not a metalloid, silicon is a non-metal. Yes, it's an anomaly, but if you will follow some good book, silicon is referred as non-metal, right? So germanium, arsenic, antimony and tellurium is considered as metalloids, right? Let's move forward. P block. After that, we have to move towards the respective D block elements. If you want to know the names of the elements, we can write this also. See, we have understood the properties of all the elements present. If you want to know the names also, you can know the names also. Okay. Group 15, what all elements are present? Group 16, 17, 18. You should remember every of the element present in the group 15, 16, 17, 18. You should remember every of them. Okay. If you want to write, we can write also. Group number 12, 13, 14, 15, 16, 17 and then 18. So group 12, that will be the group number respectively zinc group. First of all, 13. So we have these elements present: boron, aluminium, gallium, indium, thallium. You need to remember every of the element. After that, group number 14. Group number 14, remember all of the elements. Group number 15, it is very important to learn, beta. It is very important to learn all of these elements. Polonium again is a radioactive element. I am writing a star with the radioactive elements. We don't have to study the properties of these elements. And then group 18. These all are the noble gases. So you need to remember all of the elements present. General electronic configuration: NS2, NP1. Here we have NS2, NP2. Then we have NS2, NP3. Then we have NS2, NP4. Then we have NS2, NP5. And then we have NS2, NP6. You know, this respective group is considered as a stable one. It is considered as a stable one because the P subshell is having exactly half-filled electronic configuration. Exactly half-filled electronic configuration gives it the stability, because what they are exactly half filled. So you need to remember the properties related to all of these elements, the p block, the names, if there is some property of the stability. See, group 18 is stable, that we don't need to write because we all know all these things. But group 15 is also considered as stable because it is having the very stable electronic configuration of the exactly half filled p subshell, right? Let's move forward. After that, we are having the D block elements. So all these are your D block elements, which is starting from the scandium, yttrium, lanthanum, actinium, and we are moving from left to right towards the D block, which is starting from the third group. Then we have fourth group, fifth group, sixth group, seventh, eighth, ninth, 10th, 11 and 12. Combinedly, total, if I called it as, there are total 10 groups. If I call it as, there are total 10 groups. There are total number of groups which is equal to 10, which is starting from the group number 3 ending towards the group number 12. Okay, if you talk about the lanthanoids are present after lanthanum, after actinium. Do not forget that this respective group, which is the group number 3, you know that this group number 3 has total elements. How many number of total elements are present in the group number 3? It is having total number of 32 elements. How you have 32 elements in the group number 3? See, you have first of all 1, 2, 3, 4. 4 elements are already present in the group, and 14 are the lanthanides, 14 are the actinides. So 14 and 14 will give you 28, and all these 4 elements will give you the number 32. So the maximum number of elements present in any of the group is your group number 3rd. Group number 3rd is having the total elements as 32, the maximum number of elements any group can have, right? Perfect. After that, this respective group, which is the group number 12, is considered as pseudo transition elements. It is considered as pseudo transition elements. It is considered as pseudo transition elements. This group number 11 is considered as coinage. The elements present over here is used in the making of the jewelry, making of the ornaments. So they are considered as coinage metals. I will explain you the meaning of pseudo, but first I am explaining you the meaning of coinage, which is the elements which is used in the jewelry, ornaments making and all these things, right? So this is the list of the elements which is present in the D block. You need to remember every of them. You need to remember every of the M, because you know they are not asked right now very much, but in the D block elements, which is the chapter present in the class 12th of the chemistry, inorganic chemistry, maximum number of questions are related to the electronic configuration, the placement of the atoms, where exactly it is placed, group number, period number and all these things, right? So let's move forward about the properties of the respective D block elements. General electronic configuration is NS 0 to 2, N minus 1, D 1 to 10. See, if I write the electronic configuration, so I should write NS 1 to 2, N minus 1, D 1 to 10. This should be the correct electronic configuration. But you know, if you have NS as 0 and if you have NS as 1, these two electronic configurations are considered as exceptional. These two electronic configurations are considered as exceptional. Like if I say I have copper. Copper is having atomic number as 29. I write it as argon 3d5, not 3d5, that is for the chromium. I write it as 3d10 4s1. So you have exceptional electronic configuration of s1. If I write palladium, it is having electronic configuration of argon, not argon. It is having electronic configuration of krypton 4d10 and 5s0. You know, if we write this s0, that is only because of the palladium, because palladium is only element in the D block element which is having the electronic configuration as s0. So you can see with the help of these examples that yes, we are having some exceptional electronic configurations of NS0 and NS1, which gives us the change in the electronic configuration from NS1 to 2. We change it as NS0 to 2. It can be anything, right? Okay. Total number of groups. Groups is 3 to 12, and total we have, total if I ask you, there is total number of groups as 10 groups. After that we have last electron enters the d subshell. That is the definition of any of the group elements. Like if we have the last electron entering the p subshell, so it will be called as a p block element. If it is entering d subshell, it will be called as a d block element, right? After that we have transition elements. See, you have some series named as 3D series, 4D series, 5D series and the 6D series. I will tell you all these things in this respective position. See, what we are having is, this is called as 3D series. This is called as 4D series. This is called as 5D series. And this is called as 6D series. 3D series, 4D series, 5D series and the 6D series. And even we have the period number associated with them. This is having the period number as 7th. This is having the period number as 6th. This is having the 5th. And this is having the 4th period. It is starting from the 4th period, ending on the 7th period. 4th period is having the series called as the 3D series. Then we have the 4D series, 5D series, and then we have the 6D series, right? This is the order in which the series are present. Perfect. Moving towards the next point. That is, you can see the series. You can easily answer all of these. If you write the general electronic configuration, we can write the general electronic configuration for all these elements also. Like I can write over here, any of the noble gas I can write argon, krypton, xenon, and then I will write radon. So here we'll be having 3D, 1 to 10, 4s, 1 to 2, 4D, 1 to 10, 5s, 0 to 2, because this 5s 0 exception is present for the case of the palladium only, so I have written here only 0 to 2, right? After that we have 5D, 1 to 10, 6s, 1 to 2. Then we have 6D, 1 to 10 and 7s, 1 to 2. You can easily know this thing. You can easily understand this thing, that why I am writing over here this 3D or the 4D or the 5D number. This 3D, I have written 3D. You have the d electrons entering in the 4D, d electrons entering in the 5D, d electrons entering in the 6D. So these are the numbers. And I have written that this is having period number as 4th. This is having as 5th. This is having as 6th. This is having as 7th. So these number corresponds to, let's take a green color. These numbers corresponds to the period number. So there is an explanation of every of the thing present in the periodic table. I'm not writing 3D superficially. I'm not writing this 4s superficially. There is a meaning. Scandium to zinc, there is number of elements present. I'm writing 3D series because in the D subshell, the electron is entering into the 3D subshell, right? I'm writing 4s because the period number is 4th. The biggest shell number corresponding to this respective period is 4, right? Okay. I have already written over here that group number 3 contains maximum number of elements, which is 32. I have already explained. Group 3 contains lanthanides and actinoids. Very, very important. These points, these so small questions, all these points, these come directly in the examination. These points come directly in the examination. Group 12 is called pseudo transition elements. Pseudo means that they don't have the exact properties that should be associated with the transition elements. Transition element, I should explain you the definition of transition element. Listen. What exactly do you understand by the transition element? You sometimes have a question in your mind that what are transition elements, right? You have a question in your mind that what exactly is transition element. See, transition element is which is having incompletely filled. It is having incompletely filled incompletely filled d subshell, incompletely filled d subshell in ground state, incompletely filled d subshell in the ground state or any oxidation state, which is the stable oxidation state. You should have an incompletely filled d subshell either in the ground state or any of the oxidation state. But you know, zinc is having a problem. If I talk about the zinc, I should not write as an example, but if I talk about zinc, zinc is having atomic number as 30. If I write the electronic configuration, that will be argon 3d10 4s2. So in the ground state, it is having the completely filled d subshell. It will not be called as a transition element. But zinc is having only one oxidation state as zinc plus 2. So that case will give electronic configuration as 3d10. Still it is completely filled. So there is no incompletely filled d subshell either in the ground state or any of the excited state or the oxidation state. So how can I call zinc as the transition element? So it is called as a pseudo transition element, fake transition element, not having the exact properties that transition elements should have, right? You might have a question that, ma'am, copper also is having the electronic configuration. So see, copper is having electronic configuration as argon 3d10 4s1. But you know that copper is having the stable oxidation state of copper plus 2, in which it becomes 3d9, and it is having incompletely filled d subshell over here. So yes, it will be called as a transition element, and this will not be called as a transition element. I will not call zinc as transition element, but yes, I will call copper as transition element. So this is the definition of the transition element, and you need to remember this very nicely. Neither of your zinc, cadmium, mercury, copernicium, none of them, zinc, I should change the color, none of them, you call it as zinc, cadmium, mercury, copernicium, none of them is considered as the transition element. All of them is considered as the pseudo transition element. All of them is considered as the pseudo transition element, and you need to remember this very, very nicely. You need to remember this very, very nicely. Okay, moving forward. Now we have the F block elements present with us. You know that F block elements are present in the group number 3. Period number 6 is lanthanides. Period number 7 is the actinoids. But we cannot place them there. So we place them in the bottom of the periodic table, and that is the bottom present on the blackboard. Okay. So you can write over here. I should take a very good bright color. This is your period number 6th, and this is your period number 7th. So lanthanum, it starts from the lanthanum, it starts from the cerium, and it ends at the lutetium. It starts from the thorium and ends at lawrencium. Thorium to lawrencium, cerium to lutetium. Lanthanum is not a lanthanoid. Actinium is not an actinoid. You need to remember this, okay? Because last electron does not enter into the F subshell in the lanthanum. These are from 58 to 71, and these are from 90 to 103. Everything is asked where they are present, what is the name of the series starting element, end element, because you know periodicity contains very not very big questions of the F block elements. Very slight easy questions are coming in the periodicity chapter, right? Okay. But yes, the NEET examination or the JEE examination will not tell you that this chapter is from the periodicity. They will give you the combined questions. So first of all, in the periodicity, you are just understanding the basics of the F block elements. When you will reach to the F block elements of the class 12th, you will have a different explanation of so many properties of the F block elements, right? Okay. सबसे पहले, first of all, general electronic configuration. NS2 n minus 1 d 0 to 2, n minus 2 f 0 to 14. This is the general electronic configuration of all the f block elements. See, we can have f1 to 14 as the correct one, but when we have f0, that is for the thorium, so we have a exceptional electronic configuration. We have over here the exceptional electronic configuration. We have over here the exceptional electronic configuration for the thorium. Okay, perfect. Last electron enters the f subshell. Very true, because that's why only it is called as the f block element. Called as the rare transition elements because they are present inside the transition elements. They are called as inner transition elements. They are not found everywhere. They are rare transition element present inside the transition elements, inner transition elements. Okay, contains two groups, lanthanides and actinides. Okay, enters anti-penultimate shell. Now what do you understand by this word anti-penultimate shell? If I have a nucleus over here, I have this shell, this shell, this shell, and many numbers of shells are present, right? There are many number of shells present. I name it as n, I name it as n minus 1, I name it as n minus 2, and so on, right? So this shell which is present at the outermost number, which is the outermost shell, it will be called as the outermost shell. This n minus 1 will be called as, it will be called as penultimate shell, whereas this n minus 2 will be called as, it will be called as anti-penultimate shell. It will be called as what? It will be called as anti-penultimate shell, and you can see very nicely f block elements. The f electrons are filled in the anti-penultimate shell, which is n minus 2. D are filled in the n minus 1, and S is filled in the outermost, which is NS. So this is very, very important. This can also be asked. So you should know this, right? After that, we are having the names of all of the elements of the lanthanoids and all of the names of the actinoids. Do remember the names of these elements, and if you can, at this point of the periodicity chapter, if you can learn the electronic configuration of all of the F and D block elements, it will be wonderful, right? So you should learn. Okay, moving towards next, if you have to identify the position of an element, let's say I have a element which is present in the very left, that is an S block element. So let's say I have to calculate for the sodium. I don't know it is a sodium, I'm just giving you an atomic number as 11. So you will write the electronic configuration, 1s2, 2p6, then we have 3s1. So if it is the last electron is entering the S subshell, surely it's a S block element. I know that it's a S block element. So if it is written ns1, so it's a group number 1. If it is written ns2, so it's a group number 2. So it is ns1, so it will be the group number 1. And the period number will be decided by the highest principal quantum number. Period number will be decided by highest n. Whichever is highest number decides your period number. Okay, so you can simply write over here that group number is 1, whereas period number is 3. That's it. S block element, you can have any of the atomic number. If the last electron is entering the S subshell, you can have this kind of a rule. Then we have a p block element. Let's say I have an atomic number. Let's say I have an atomic number as, let's say 16. So I will write electronic configuration, 1s2, 2s2, 2p6, 3s2, and then I have 3p4. For sure I have 3p4. So first of all, I need to have the period number. So which is the highest n. N is 3. So the period number will be 3. Highest n will be 3. So period number is 3. This is giving us the period number. This is giving us the period number. What about the group number? Just add for the group number the S electrons plus P electrons plus 10. This S and P electrons will be for the outermost shell. This S and P electrons will be for the outermost shell. So outermost shell S electrons is 2 and the P electrons is 4 plus 10. So it is coming out to be 16. So you can simply write over here that the group number is 16. Just for the group number, add S electrons, the P electrons 10, and that will be the group number. The highest N, the highest shell number, the outermost shell, period number. You can relate all of these words with each other, right? After that we have D block elements. Let's say I have an atomic number. Let's say my favorite for the D block elements is 25 atomic number. Electronic configuration. Argon 3d5 4s2. Or you can write the total open electronic configuration also. So just have a look at the highest principal quantum number, which is 4. So simply you can have your period number as 4. You can simply write your period number as 4. Very easily you will get your period number. What about the group number, ma'am? So for the group number, just add S electron and D electrons. How many S electrons you are having? 5. How many D electrons? No. How many S electrons you are having? 2. D electrons 5. So 2 plus 5 gives you 7, and that is only your group number. 7 will be your group number. So you can easily calculate for the D, P, S. These are the rules. Okay. After that we are having, see, for the elements which are having the atomic number from 104 to 118, group number is decided by the last 2 digits. Period number will be 7. Period number for all these will be 7. Period number will be 7. And for the group number, let's say I have a group number 117. Let's say I have atomic number 117. So for sure, group number will be 17. So you can have a look at this and you will be easily able to calculate the group number. 7th period contains elements having atomic number 87 to 118. This can also be a click to your memory. Okay. 58 to 71 is lanthanoids. You know that group number will be 3 and period number is 6. 58 to 71, 90 to 103. I have told I think 10 to 15 times in this class only about the lanthanides and the actinides, right? So this is a very important page for you. Do not forget this. Now we are moving towards the periodic properties. We have so many kinds of a radius present for us. Covalent radius, metallic radius, and the van der Waals radius. You know all these kinds of radius. The most important ones for us is the covalent radius. So what do you understand by a covalent radius? See, I have an atom. First of all, I am explaining you the covalent radii. We have to understand about the covalent radii. Now what do you understand by the covalent radii? Let's say I have an atom covalently bonded to other atom by sharing of electrons. So I have a distance d over here. So radius covalent will be this distance divided by 2. Okay, covalent radii. What about if I have to calculate the metallic radius? Metallic radius is calculated for the metals. It is specifically calculated for the metals. Like I have a block of a metal over here. I have metals present inside it. So the distance between the two nearest metals, that will be d. So metallic radius will be this distance divided by 2. Obviously they are not the covalent bonded, but whatever be the nearest distance between them, that divided by 2 will give you the metallic radius. And what about the covalent radius? See, there are so many things associated with this, but I am giving you the very pinpoint information, the direct information. Just know this much, you will be able to solve all of the questions, right? Van der Waals radius. Van der Waals radii. See, van der Waals radii is specifically for the noble gases and for the homodiatomic gases. Hai na? This is applicable for the noble gases, specifically for the noble gases and homodiatomic gases. Homodiatomic gases. Let's say I have a molecule of Cl2. I have a molecule of Cl2. This is a Cl2 molecule. So the nearest distance between these two molecules, This distance I call it as d. It can be anything. It can be anything. I have made this much. It can be like the nearest whatever is possible. I have drawn that only. Okay. So van der Waals radii will be equal to this distance divided by 2. See, this molecule is Cl2. This molecule is Cl2. So they are covalently bonded to each other. I can have a covalent radius also present here only. I can have the covalent radius also present over here only. That will be, this covalent radius will be d divided by 2. This will be the covalent radius, and two molecules of Cl2 will have a minimum distance between each other. That distance divided by 2 will give me the van der Waals radii. So I just want to ask you a simple question over here. What will be the order of all these radii? Van der Waals radii, the highest one, then I have the metallic, and then I have the covalent. So just remember this order. I'm not telling you to remember anything else. Just remember this order. That's it, right? Moving towards the next. Now I'm moving towards the atomic radii. In the case of the atomic radii, we usually use, 99% we usually use the covalent radii, right? So what happens when you are moving from left to right? What happens when you are moving from left to right? See, as you are moving from lithium to beryllium to boron, your electronic configuration is what? 1s2, 2s1, this is 1s2, 2s2, this is 1s2, 2s2, 2p1. So what is happening is, you are having the electrons increased in the same shell. Here you are having electrons increased in the same shell, right? In the same shell. Here you will be having some more electrons present, but in the same shell. So you can see, when we are moving from left to right, electrons are increasing in same shell. Whenever you have electrons increasing in the same shell, your Z effective, which is the effective nuclear charge. You have studied the effective nuclear charge in the chapter structure of atom. Effective nuclear charge. Effective nuclear charge. You know that Z effective is effective nuclear charge. It increases by 1 unit. With every of the electron increasing, see what happens. You have the same shell. The electrons are increasing in the same shell. Simultaneously, protons are also increasing. So one increase, one proton will attract. Other electron is increased, other proton is also increased. So it will attract more. If you have the same shell in which electrons are increasing and the protons are also increasing simultaneously, protons has a good hold to attract the outermost shell towards itself. Greater the number of protons increase simultaneous to the electrons, size will be decreased, but there is a condition that electrons are increasing in the same shell. If your shell is changed, the condition will be something different. Okay, done? So please remember this, that effective increases by 1 unit when you're moving from left to right to every atom. Effective nuclear charge increases by 1 unit, size decreases, and you'll get the order which is present over here. But one thing I need to tell you is, why neon is coming over here. If you have the decrease in the sizes, if you have for the second period, I have sizes as lithium, beryllium, boron, carbon, nitrogen, oxygen. So why it is the case that neon is coming over here? Why? Because for the neon, I always consider my van der Waals radii. I always consider my van der Waals radii, but in the case of the rest of the elements, I consider only the covalent radius. And you know that van der Waals radii is greater than covalent radius. You know very well that van der Waals radii is greater than the covalent radius. So there is no, There is no doubt in this case that yes, neon will come over here only. Neon will come over here only. Neon will be at the first present, and same is the case with the hydrogen and helium. And same is the case with the hydrogen and helium. You can simply see that helium is greater than hydrogen over here. Why? Because even they are present very near to each other, right? So hydrogen will be having the radius covalent and helium will be having the radius as van der Waals. So do not forget this thing, because this is required in the states of matter chapter when you are studying the van der Waals constant A and B. There also we need this data. Okay, so when you are moving from left to right, size decreases. We know all these things. Moving from top to bottom, there is no issue. When you're moving from top to bottom, obviously size will increase, because you're having the, now the shell is changing. You're having the increase in the number of shells. So size will increase. When you're moving from, let's say, lithium, sodium, potassium, rubidium, cesium, when you're moving from top to bottom, your size increases. As you can see, lithium having the electronic configuration as 1s2, 2s1, sodium 1s2, 2s2, 2p6, 3s1. You can simply see there is a change in the shell number. There is a change in the shell number. So your size will increase according to that. Okay, so size will be increased. This is followed by everyone. When you're moving from top to bottom, this is followed by everyone. There might be some exceptions also. That also I have included. Right now I have just written the normal order. Top to bottom, size increases. Perfect. Let's move forward. Ionic radii. Now, atomic radii we have considered the covalent one. Now the ionic radii. Now you have become the ion. What will be the case now? See, whenever you have an ionic radii, the order will be like this. Anions will be having the greater number of electrons. See, I'll tell you one small thing. Whenever the number of electrons are greater than number of protons, your Z effective decreases, sigma increases, size increases. Do not forget this thing. You have studied that in the structure of atom chapter. I have just written the bullet points now. Just remember one thing, this thing, and just do your questions. After that, if you have number of protons greater than number of electrons, then your Z effective, that is the effective nuclear charge, that is a charge experienced by the outermost electron from the nucleus, considering all the shielding, all the whatever is present, whatever electrons is present, what they are doing. This is your nucleus, this is your outermost shell. This nucleus is trying to attract the outermost shell. It is giving its charge to the outermost shell, but the electrons present in between are not allowing that. They are present as shield. They are screening that. They are shielding that. So the outermost electron is not able to get the proper charge of the nucleus, the proper attraction of the nucleus. So whatever charge this respective outermost electron is getting, whatever left electronic charge it is getting, is called as effective nuclear charge. You know, there is an equation, Z effective is equal to Z minus sigma. What is Z effective? Whatever charge, whatever left charge that outermost electron is getting is Z effective. Z is the actual charge it should get. If I remove all of the electrons from the between, what charge it should get is the Z. And the sigma is the problem. Sigma is the number of electrons present in between that are not allowing the outermost electron to get the proper charge of the nucleus, is included in the sigma. Okay, you know all these things very nicely. So whenever there is a protons increased, okay, Z effective increases, sigma decreases, size decreases. Okay, remember this. Z effective. What is Z effective? Z effective is the actual charge experienced by the outermost electron after all the repulsive interactions present due to the inner electrons. Okay, greater the Z effective, greater is the charge experienced by that outermost electron, so it will attract that more. What is Z effective? This respective outermost electron can be attracted more by the nucleus, so it will be shifted towards it. So size will be decreased. More the Z effective, less is the size. more the Z effective, less is the size. Please remember this. Relate this with the protons and the electrons. See, now that it's the time to apply all these things. You know what is shielding effect, what is happening, not happening, what is the value, all the values not never asked in the examination, but you know how to calculate with the help of the Slatter's rule. Now, just follow these two and solve your questions. Okay, perfect. Okay, so anion, what is happening? Always the size of the anion is greater than neutral atom and greater than cation. Okay, let's say I have an example. I have, let's say, any of the thing. I have I negative, I have I positive. So always the size order will be followed by this, because you know that in the case of the anion, the number of electrons is greater than protons, and cations, protons is greater than electrons. Okay, so you can simply say when the protons is greater, size will be small. You know all these things. Just relate with that and get your answer. Anion, neutral, cation, anion, neutral, cation. Greater the number of electrons, greater will be the size. Greater the number of protons, less will be the size. Okay, you can calculate with the help of E by P ratio also, but that takes time. You will calculate electron, proton, you will calculate the ratio. Why to make the task tedious? Just have a look, right? Okay, if you have a greater charge of, like if you have this kind of a thing, let's say I have F minus 2, I have I cannot have the F minus 2, I have Fe minus 2, I have Fe minus 3, I have to write the size order. So negative ion, so the negative ion will surely have the greater size. Greater the negative charge, greater the number of electrons, greater will be the size. Okay, so the size order will be 2, 1, 3. So just use this, nothing else you have to do, right? Isoelectronic species. What are isoelectronic species? The species which have the same number of electrons. So first you need to calculate the number of electrons present in the ion or the neutral atom or whatever. Okay, so negative, neutral, positive. Always you have to follow that. Anion, neutral, cation, negative, neutral, positive. Because when you have negative charge, you have greater number of electrons, you have bigger size, you have less Z effective, you have greater sigma, and we have as a result increase in the size. Greater the negative charge, greater will be the size, then neutral. If you compare the positive charges, this is having greater positive charge, it is having greater number of protons, less number of electrons. Greater the number of protons, less is the size. Okay, remember this thing. All of them have 10 electrons. All of them have electrons equal to 10. All of them have electrons equal to 10. First you have to see the negative one. Greater the negative charge, greater the negative charge, so greater will be the size. Greater the positive charge, you will have less as your size. Just for the isoelectronic species, remember this thing, nothing else you need to remember. Just remember these two things. You have an example over here, just follow this and get your answers, right? Let's move forward. Which one of the following is the correct order of the size of the iodine species? I have already explained you. I negative, I and the I positive, and anion, neutral, cation. Okay, chalo. Exceptions. See, I have written exceptions over here. As we will study the lanthanoid, actinoids, D block, P block, all these things, so we will discuss all these things in a more deeper manner. But right now I have written the exceptions. If you are trying to solve the questions related to the periodicity, just see them and give your answers. Exceptions. Group 13 is having a very exceptional order of the sizes. See, if you see the group 13, boron, aluminium, gallium, indium, thallium. This is the size. You will follow what? You will think, ma'am, thallium the highest one, then indium, then gallium. Then ma'am, why this problem is present? Then why this order of aluminium and gallium is changed? They are almost same, because beta, gallium is having d electrons, which is having the poor shielding effect. You know the order of shielding effect. You know that. I hope you know that. Poor shielding effect. What is the order of sigma? What is the order of sigma? S, P, D, F. This is the order of sigma, and you need to remember them. The D and F is having the very poor shielding effect. D and F combinedly have very poor sigma. Con, D and F, very poor sigma. Do not forget this thing. Do not forget this thing. For the D block elements, there is some exception present. When you are moving from 3D to 4D to 5D, the size of the 4D series and the 5D series is almost constant. If I talk about the 3D series, then you move for the 4D series, then you move for the 5D series. Always remember the order of the size, the exceptional order. The 4D size is almost equal to the 5D size. You know all these things. You have studied this in the D block elements. You have studied lanthanoid contraction. There you study that 4D and 5D elements are having almost equal size. If you want to know, I can have a very quick explanation. Very quick. You will be having a small revision over here. You know what happens is, this group, these elements, this 4D series and 5D series is having a very similar sizes. When you're moving from 3D to 4D, there is a significant increase in the size, But when you're moving from 4D to 5D series, very less increase in the size. Let's say if this is 100, this is 200, and this is 201, or maybe 200 also, maybe 199 also. There is so similarity in the sizes. But what is the reason? Reason is because when you are moving till cadmium, no problem. After cadmium, there is lanthanum, and after lanthanum, there is 14 elements in which size is it decreasing one by one through one unit. With every F electron, size is decreasing. Lanthanide contraction. You have those 14 elements over here. See, I am writing these 14 elements in the middle, in the below row, but they are actually present over here only, na? They are present over here only, na? If I place them over here, they will have the decrease in the size. After that, hafnium is coming. Hafnium is having the size very less. It is coming out to be equal to zirconium only. है ना? Tungsten is coming out to be molybdenum only. This is a result of this lanthanide contraction, that after that cerium to lutetium, we have hafnium that is having size equal to the 4D series due to lanthanide contraction. If these 14 elements are not present, then this would not be the result. Okay, so remember this thing. Okay, I'm not getting into so much deep. I'm just giving you the one shot, whatever I can explain you. I think you people have already done all these things. Okay, we are having the one short lecture. I'm trying my level best that I can give you the maximum number of things I can, right? Okay, so what I'm telling you is size of 4D and 5D is almost same, okay? And 3D is having greater size than 4D and 5D series. Do not forget this. Do not forget this, okay? Always you have to remember this thing. But this is not followed. But that is not followed for these elements. What I'm telling you, this is not followed. This is not followed for these elements. This is not, because lanthanoids are coming after lanthanum. So why I will write all these exceptions for scandium, yttrium and lanthanum? These are coming below this respective lanthanoids, na? So this exceptional trend of 3D, 4D and 5D size, 4D, 5D size is similar. That is not, I have already made this pink color line over here. So to tell you that this exceptional order is after zirconium, after hafnium. Okay, perfect. Okay, perfect. Now, group 3 has normal trend. I have told you. Lanthanoid actinoids normal trend when you are moving from cerium to lutetium, when you are moving from thorium to lawrencium, you will have decrease in size, okay, and that is due to lanthanoid or actinoid contraction. Okay, lanthanoid and actinoid contraction. There is no exception in this lanthanoid. There is a normal decrease in the size. You can see simply, when you are moving from cerium to lutetium, you are moving from left to right. What is the exceptional thing in that? You are moving from cerium to lutetium. You are moving from left to right. Size will be decreased. What is the unusual thing about this. Although NCRT highlights lengthenoid contraction, but we know we are moving from left to right. What is the so much deeper sense in that? We know that. We know that, right? So let's move. Which of the following has larger size? Do remember, this is Amitabh Bachchan, very big in size. Okay, do not forget this. H negative is just remember as an exception. Okay, whenever I'm writing an exception now, I will make 2 stars so that you can remember that yes, ma'am have told us H negative is present, so it will be having the bigger size and it is an exception. We don't have to forget that, right? Perfect. Identify the wrong statement in the following. Wrong statement. Atomic radius of the elements increases as one moves down the first group of the periodic table. Okay. Atomic radius of the elements decreases as one moves from left to right in the second period of the periodic table. Among isoelectronic species, smaller the positive charge on the cation, smaller is the ionic radius. Smaller नहीं होगा बेटा यहाँ पर, ये गलत है. It will not be the smaller. Amongst isoelectronic species greater the negative charge, larger is the ionic radius. So that is true. If you have isoelectronic species greater the negative charge, larger is the radius. This is true. This is wrong. What about the second one? Atomic radius of the elements decreases as one move from left to right in the second period of the, you have for the all of the periods, it is not specifically for the second periods. And okay, atomic radius of the elements increases as one move down the first group. It is, we cannot say that it is specifically for the first group, but you have to answer according to the question. Okay, obviously previous question, wrong statement, there will be only one wrong statement, that is this one. You have to just don't think that it is talking about the second period, so only for the second period. No, because same kind of a anomaly question is in the anomaly point is in the A also. Here they are talking about only the first one. Here they are talking about only the second one. So just do not stick to the concepts. Sometimes we have to segregate between the points also. What is the question demanding from us? Right? Move forward. Okay. From the following pair of the ions, which one is not an isoelectronic pair? No problem. You have to calculate for the isoelectronic pair the number of electrons. Okay. O2 negative, F negative is isoelectronic. You can simply calculate. This is isoelectronic. How? Because oxygen is having 8 plus 2, that is equal to 10. Fluorine is having 9 plus 1 equal to 10. Iron is 26, so it will be 24. Manganese 25, so it will be 23. No, correct. Manganese 25, so it will be 23. Iron 26, so it will be also 23. Sodium 11 minus 1 equal to 10. Magnesium 12 minus 2 equal to 10. So which is not? So answer C is not an isoelectronic. B and A both will be isoelectronic. You can simply calculate with the help of the atomic numbers. Okay. Let's move forward. The species argon, potassium and calcium contain the same number of electrons. So they are isoelectronic. They have already written that. In which order do their radii increases? You know, greater the negative charge, greater the size. Greater the positive charge, smaller is the size. Neutral atom will be present in the between. Okay. So calcium is having the greater charge, so it will have the less size. So your answer will be option number B. So option number B will be the answer. Greater the positive charge, greater the positive charge, less is the size. Greater the positive charge, less is the size. Perfect. Let's move forward. Now, ionization enthalpy. Very, very important. You know, it is very, very important. Ionization enthalpy. Now, what is happening over here is, first we have to discuss the definition, and before that I have to drink the water. Just 1 minute. Okay. What is ionization enthalpy? You cannot simply say removal of electron. No. Energy required to remove the outermost electron from an isolated gaseous atom. You cannot remove electron from the bonded state. You cannot remove electron from the solid or the liquid state. You have to take the gaseous state. So, amount of energy required to remove outermost electron from an isolated gaseous atom or the ion, every word have its meaning. And that is important to mention that word with its meaning. Okay. So, it's measured in the joule per mole, kilojoule per mole, electron volt per atom. Okay, first of all, whenever I talk about the ionization process, I take a element X gaseous, I supply some energy, X positive gaseous I will get with the removal of one electron. With the removal of one electron. Always I have to supply energy, so this delta H ionization will be a positive one. So I will call it as endothermic process. What I will call it as? I will call it as endothermic process. But not all ionization process are endothermic. Let's say I have an anion. I have this anion X2 minus gaseous. If I remove electron from this, I don't have to supply any energy. This ionization process, this removal of electron is itself. I don't have to supply any energy. So please consider this. Do not have any of the doubt in this that always and always ionization process is endothermic. No, because you know that there are a greater number of electrons present. They will repel each other. They will always think that they move out. We are having this interelectronic repulsions. Hai na? They will feel this now. So they will get any of the chance that extra electron will be removed itself. So you don't have to supply any energy. So that process will be exothermic. So it can be endothermic and it can be exothermic. Both it can be. Okay. So what is IE1? What is IE2? Whenever you are removing first electron, let's say you are removing first electron, X positive gaseous plus electron, that will be IE1. Okay. But if you are removing another electron you are removing from the same ion, X positive gaseous, so that will be IE2. Do not say this word ionization enthalpy. That is having no significance. IE1 or IE2. IE1 first electron, IE2 second electron. Okay. Successive ionization enthalpies are always higher. What they are talking about? They are telling that, let's say I have X gaseous atom. I remove an electron, I am forming X positive gaseous. Okay, I am removing other electron, I am forming X plus 2 gaseous. This will be called as IE1. This will be called as IE2. And if I remove another electron, this is IE3. Okay. Now you tell me, this is neutral, this is smaller size, more positive charge, more smaller size, more positive charge, more smaller size. If I write the order of the sizes, the biggest one will be X, then X plus 1, then X plus 2, and then X plus 3. Hai na? You know all these things, and you know this also, that greater the ionization energy, less is the size. If you have greater size, you have greater ionization energy. So that's why your size is getting decreased with every removal of electron. So you have to supply more energy na, to remove the further electron. So what is the big thing? You have to remember this. You have to remember this. Do not forget, successive ionization enthalpies are always higher. Okay? Are always higher means that you have to supply a greater energy to remove the further electron. Okay. Now we are having the factors on which ionization enthalpy depends. Size increases, ionization enthalpy decreases. With no problem. Size is inversely proportional to ionization enthalpy. We know all these factors. We are just having a quick look on that. Effective nuclear charge increases. Ionization, what is this? Z effective increases. So size decreases. So ionization enthalpy increases. What is the big thing in that? We know this because you know whenever there is an increase in Z effective, that means that protons are increasing and the electrons are decreasing. If protons are increasing, your size is getting smaller. So ionization enthalpy will increase. Screening constant increases, ionization energy decreases. You know what is that? You know there is an equation, Z effective is equal to Z minus sigma. So they are talking about this sigma. Greater the sigma, greater the size, and less is the ionization enthalpy. Do not forget this thing, because whenever sigma is increased, the electrons between nucleus and the outermost shell increases. They are shielding. So the attraction towards the outermost electron decreases. Electron can be removed very easily. So sigma increases, ionization enthalpy is decreasing. We have so much bigger wall of the electrons present in between the nucleus and the outermost shell. There is very less Z effective the outermost electron is getting. Electron will be removed very easily. Right? Ionization enthalpy increases for half filled and fully filled. What is the big thing in that? You tell me. What is the big thing in that? Because electronically, electronic configuration is stable, na? Half filled and fully filled electronic configuration is considered as stable. So it is stable. So why electron will be out? It will not go out easily. Ionization enthalpy increases. Okay. Left to right. What happens? Left to right. Left to right when you are moving, so size decreases, ionization enthalpy increases. Normal order we are following. We are not doing something very exceptional. For noble gases, van der Waals radii is considered in a period. They always have a high ionization energy. If I write the order, so what will happen? See, if I write the order, lithium, then beryllium, then boron, then carbon, nitrogen, oxygen, fluorine. If I talk about the ionization enthalpy order, so what should be the case? You will expect this, but you know that there is an exceptional order. Problem is here, the change will be boron and beryllium. Here there will be change oxygen and nitrogen, and also neon will come over here. Why this is so? Because boron is having electronic configuration as 1s2, 2s2, 2p1, whereas beryllium is having 1s2, 2s2, which is completely filled. You have just we just had a conversation that half filled and fully filled electronic configurations are stable, so the removal of electron will be hard. Okay, so completely filled, so it will be considered as stable, so ionization enthalpy will be high. Okay, what about the oxygen and nitrogen? If I take the electronic configuration of oxygen, it will be 1s2, 2s2, 2p4, and if I talk about the nitrogen, it will be 1s2, 2s2, 2p3. It will be what? It will be 1s2, 2s2, 2p3, and that is considered as stable. 2p3 is exactly half filled. You know all these things. You know all these things that 2p3 is exactly half filled. So the removal of electron will be hard. 2p3, it will be stable. Ionization enthalpy higher. Ionization enthalpy higher. Okay. What about neon? We have the high ionization enthalpy because we have a very different reason, because we are very stable. We are fully, completely, with no exception, we are fully filled. We always have NS2, NP6. Why we will remove electron? What is the need? We have a authority of God that we don't require to react with anyone else. So why we will release electron? Right? So high ionization enthalpy of these. So this is the order you have to follow, and don't forget this order. Okay? Including the exceptions. Okay, let's move forward. Top to bottom, ionization enthalpy decreases because you know that top to bottom your size increases. So for sure your ionization enthalpy will decrease. We know this. There is no exceptional trend present over here. Size is obviously increasing due to the increase in the number of shells. Okay. Exceptions. There are exceptions. If you go towards boron, aluminium, gallium, indium, thallium, this is so exceptional trend. I have already told you that group 13 is a most heterogeneous family. Family which is having number of exceptions present. Full of exceptions present. है ना? So ionization enthalpies, top to bottom size increases. Okay. Okay, we have exceptions in aluminium and gallium. Now you're telling that after boron, thallium will come. But why? Thallium is having D and F electrons, whereas gallium is having D electrons, and you know that D and F electrons are having the poor shielding effect. They are having the poor shielding effect. Ma'am, why do you write always this poor shielding effect? What do you mean by that? Just tell us in some very short words. See, whenever we consider that some of the orbitals or subshells is having very less shielding effect, what happens is that nucleus and the outermost shell is present. There are some electrons present in between which are having very less shielding effect. So that wall will be decreased. Just understand in what way I am explaining you, okay? Just forget everything. The wall will be decreased, okay? Number of electrons are also increasing. Number of protons are also increasing, okay? The electrons which were present and which were present as the walls, now the wall is decreasing because they have poor shielding effect. Number of protons but have increased simultaneously in the nucleus, so nucleus can have a good charge of it on the outermost electron. So it will affect the property of that outermost electron. So that's why thallium is not having the change in the size, but in the case of the D and F electrons are present in that, it will have a very less wall. The protons will attract that outermost electron very effectively, and it will require very large amount of energy to remove that outermost electron. That is the meaning of the poor shielding effect, if I explain in very short words, right? Okay. For D block elements, I have told you right now that the size is 3D is greater. 3D is less than 4D, and 4D is almost equal to 5D. I think I have written the order like this only, है ना? Like this only. Just a second. I think, see, I have written this only over here. That's why it clicked into my mind that 3D, 4D and 5D beta will be exactly equal. Obviously it will be greater, but 3D will be less, na? It is above. So we are here. Okay, so we have written over here the order of the size will be like this. So if you compare the 3D and 4D ionization enthalpy, so ionization enthalpy will be larger for 3D as compared to 4D, because 3D is less in the size, 4D is bigger in the size. You can see over here. But what about the 4D and 5D? See, 4D and 5D is having ionization enthalpy order as this. 4D is having what number of electrons present? It is having the electrons present as 3D and 4D. In the 5D series, we have 3D series electrons, 4D series electron, 5D series electrons, and the 4F electrons. We have all of these electrons present. So they have poor shielding effect of only these. They have poor shielding effect of these many of the electrons present. So like 10, 20, 30, 44 electrons are having very poor shielding effect. Those all electrons will be down for the 5D series elements. Nucleus will have a proper charge of it on the outermost electron. It will attract the outermost electron very effectively, and the removal of that electron will be very hard. है ना? So remember this thing, that 5D will be having the greater ionization enthalpy as compared to the 4D. So what will be the order? Always remember, the order will be first 5D, then 3D, and then 4D. This will be the order of the ionization enthalpy for your D block elements when you are moving from top to bottom. We will discuss in the deeper sense in the D block elements in the class 12th when we will be having the class 12th, but this much is fine. I think you can relate with my words, what I'm telling you, and that is more than sufficient, I'm telling you, okay? But you know that there is a mercury which is present in the 5D, zinc is present in the 3D, and cadmium is present in the 4D, and third group have the regular trend. If I talk about the size, I have already explained this thing. So lanthanum is having the largest size, then yttrium, then scandium. So the ionization enthalpy will be greater for the scandium, then yttrium, and then lanthanum. Okay. Everything I have included in the ionization enthalpy. You don't need to learn or go anywhere else. Anywhere else. Just follow this. Okay. Let's move forward. For the second period elements, the correct increasing order of the first ionization enthalpy. For the second period elements, the correct increasing order. No problem. What is the problem? There is no problem. Include the exceptions. Yes, neon is correct. Beryllium boron exception is included. Yes. Everything is included. What is the problem over here? Here there is a problem. This is correct. This is incorrect. This is correct. So correct order is option number B. First ionization enthalpy we have already discussed. See, these questions are coming in the examination. So easy questions are coming in the examinations. So let's move towards the next question. The ionization potential of lithium is this. The energy required to convert 70 milligram of the lithium atoms in the gaseous state in the lithium positive ions will be. So 70 milligram they are telling you. So convert that into the moles first. So 70 into 10 to the power minus 3 will be the gram. Atomic mass, take it for the lithium as 7. So it will be coming out to be 10 to the power minus 2. So 520 kilojoule per mole will be for the 1 mole. Okay, if it is written per mole, that is for the 1 mole. Okay. So for the 1 mole, energy you have to use is 520 kilojoule, and for the 10 to the power minus 2 mole, the energy will be 520 kilojoule divided by 1 into 10 to the power minus 2. The answer is in the kilojoule, so just take it as 5.2 kilojoule. So answer will be option number first, right? So this is how you have to solve this question. Next we have highest amount of energy will be required for the removal of electron from. See, the answer will be S. This is based on a factor which we never consider when we are solving the questions of the ionization enthalpy. We never consider. Okay. There is a effect which is known as penetration effect. There is an effect which is known as penetration effect. What is that effect? That the most near to the nucleus is S, then P, then D, and the F. So the removal of electron will be harder, which is nearer to the nucleus. If I write the nucleus over here, okay, if I'm just making a sign of the nucleus over here, the nearest will be the S, then P, then D, then F. So the S will be more attracted towards the nucleus. So removal of electron will be harder from that respective orbital or the subshell. Okay, so answer is S subshell. Okay, let's move forward. The successive ionization energies for elements X is given. See, now this question you have to solve. What they are telling you in this respective case is, okay, ionization energy 1. So X gaseous is converted into X positive gaseous. Ionization enthalpy 2. X positive gaseous is converted into X positive plus 2 gaseous. Then X positive plus 2 gaseous is converted into X plus 3 gaseous, and X plus 3 gaseous is converted into X plus 4 gaseous. So these all processes are happening in this case. Okay, 1, 2, 3 and 4. And for that all the processes, the amount of energy is required is given over here. So what you have to do, you have to make the difference. First you have to do for the IE4 minus IE3. So it will be 1400 minus 1100. Then what you need to do, IE3 minus IE2, that is 1100 minus 820. After that IE2 minus IE1, and that will be 820 minus 250. So when you will calculate the maximum difference will be coming out in between 820 and 250. First you need to calculate which will be the having maximum difference. Okay. Once you find out that, just have an eye on this. The smaller the number, you have two numbers over here. One is IE2 and one is IE1. The smaller number is 1. That means it has valence electrons equal to 1. That means that it has valence electrons equal to 1. Okay. So what will be the answer? Find out the number of valence electrons for the element X. The answer will be 1. Just this much you have to do in this respective question. Okay. So the valence electrons will be 1. You can calculate the difference. This is coming out to be 300. This is coming out to be 280. And this is coming out to be around 570. If we calculate the exact. So smaller the number, that will be the number of valence electrons. Let's move forward. With which of the following electronic configuration an atom has the lowest ionization energy? See, you know that on what factors the ionization enthalpy depends. This question has come in the NEET examination and this is very, very easy. All of these have the shell ending towards 2p. This is the one which is having the greater number of shells. So the lowest ionization energy will be associated with this only. So we have to just see the shell number and we are reaching towards the answer. Now we are moving towards the electron gain enthalpy. What do you understand by electron gain enthalpy? The energy required or the energy released when an atom accepts the electron, right? What is happening? Let's say if I accept an electron, X positive, not X positive, normal this X gaseous atom, is it accepts an electron, it forms X negative gaseous. So there can be a case that energy can be released. There can be a case that energy can be released. That process will be exothermic. So I will call my electron gain enthalpy as negative. Okay, energy will be released when the acceptance of electrons is easy. But what if I say that energy will be required? Energy will be required for addition of that electron. So the process will be endothermic. You have to supply the energy for the acceptance of electron. So that electron gain enthalpy will be positive. Okay. It is measured in the electron volt per atom or kilojoule per mole. It is measured in these two units, right? After that, if I talk to you about the electron affinity. You know, electron affinity simply means that the tendency to add electron in itself, tendency to accept electrons, nothing else. We don't have to talk in terms of the energy barriers over here. Just can you accept the electron? You have greater electron affinity. You cannot accept the electron. You cannot easily accept the electron. You have a very less electron affinity. So you have to talk in terms of electron affinity like this. Okay, I'm just telling you in the very layman language. Okay, but there is a relationship between electron affinity and the electron gain enthalpy. They have a difference of this inverse relationship. Let's say if something is having electron gain enthalpy as X, its electron affinity will be minus X. So you have to remember this relationship. This can be directly also asked. Okay. Electron gain enthalpy can be negative, can be positive. I have already told you that this can be exothermic, endothermic. If energy is released, it is negative. If energy is absorbed or you have to require energy to add electron gain enthalpy is positive. I have already told you. Successive electron gain enthalpies are always positive. Now what do you mean by that? That means, let's say I have an atom which is X gaseous. You accept an electron into that, it becomes X negative gaseous. You add one more electron over here, X minus 2 gaseous. You add one other more electron over here, it is X minus 3 gaseous. Now if I ask you about the successive electron gain enthalpy, see, once you have added an electron into an atom, it is already having more number of electrons, and those electron, that extra electron is creating inter-electronic repulsion inside. Now you are trying to add one more electron. Already there is so much inter-electronic repulsion present, and you are trying to add one more electron. How you will be able to add it easily? Okay, so you have to supply energy to add that extra electron, that another successive electron. You have to supply the energy. You know, if there is a neutral atom, you will add one electron. Let's say you have just added one electron. That electron is creating inter-electronic repulsion. It is standing on the door of the atom, that I will not allow any electron to enter. Now you're trying to enter another electron. So you have to push this electron inside, then only the other electron will enter, right? So that pushing requires energy. You have to push, you have to supply energy to add another electron, because already there is inter-electronic repulsions present, okay? So always remember this, when you are moving from this to this to this, successive electron gain enthalpies are always positive. You know, that means that if I say this process, if I say x gaseous to this, you are having as X negative gaseous, your electron gain enthalpy, let's say it is 50. That means you have to, that energy is released, like minus 50 kilojoule per mole energy is released. But if you are adding X negative gaseous, you are adding one more electron, you are making X minus 2 gaseous, then beta electron gain enthalpy will be positive and very much positive. If you are adding another electron, again you are adding another electron, it will be X minus 3 gaseous. Electron gain enthalpy in this case will be plus 200. This much amount of energy you have to supply to add this electron. Reason, you know, there is already inter-electronic repulsion. You are again adding the electron. So how it will add easily? So this is the meaning of the statement. So you have to remember this. The further processes will be endothermic, right? Okay. After that, we have a relationship between electron gain enthalpy and the ionization enthalpy. See, if you're talking about the electron affinity of A, that means you're talking about the ionization enthalpy of A negative. That means, let's say, if I have an atom A, you are accepting electron into that, it is forming A minus gaseous. And if you are removing A minus gaseous electron into the electron from the A minus gaseous, you will form A gaseous plus electron. This process will be electron gain enthalpy, and this process will be ionization enthalpy. So they have a relationship of negative. They will have a relationship of the negative sign. If you having the energy released as minus x, so you have to supply this much only amount of energy to release that electron. You have added the electron, some energy is released. If you want to remove that electron, that much amount of energy you have to supply. So the electron gain enthalpy of X will be negative to the electron ionization energy of I minus. This is the meaning of the statement. Like, there is a neutral atom. I have supplied energy and I have added the electron into that, or maybe energy is released, whatever is the case. Electron gain enthalpy positive, negative, we are not talking about that. Okay, you have just added an electron into an A atom. Okay, if you want to remove that electron, same amount of energy you have to supply. Whatever energy you have used in entering that electron, you have to supply the same energy to remove that electron. This is the meaning of this respective statement. Okay, now let's move forward. And yes, same will be the case of this also. Same will be the case of this also. Okay, let's say you have ionization energy of A. Let's say ionization energy of A is this. A gaseous is forming A positive gaseous plus electron. Now this process is ionization enthalpy. You are accepting A positive gaseous, one electron, and you are forming A gaseous. Now this is electron gain enthalpy. So they will be having relationship with each other with a negative sign. This only means, like, it's a very simple statement. You are removing an electron, है ना? You're forming A positive gaseous. If you want to add that electron again, you have to supply that much amount of the same energy. So these relationships are defined on the basis of this statement. Okay. Now, factors on which electron gain enthalpy depend. Let's say I move from top to bottom. Top to bottom, negative electron gain enthalpy decreases. Now, what do you understand by the negative gain electron electron gain enthalpy and the electron affinity. Whenever we talk about the negative electron gain enthalpy, that means every of the electron gain enthalpy, like if you add electron into the lithium, sodium, potassium or cesium, everybody wants electron. That means that they have negative electron gain enthalpy. You can add easily the electrons, okay? So they have a negative sign. Greater the magnitude, greater you have the power to accept the electrons. This is having the lowest magnitude, so it is having the least tendency to accept electron. Highest magnitude, highest tendency to accept electrons, and you have more tendency to accept electrons, that means your electron affinity is high. So when you are moving from top to bottom, your electron affinity decreases, and your negative electron gain enthalpy, whenever it is written negative electron gain enthalpy, that means electron affinity, because you know na electron affinity is negative of electron gain enthalpy, so they have equal meaning. They have equal meaning, right? So simply you have to just pick these bullet points in your head, that whenever you are moving from top to bottom, your electron affinity decreases, negative electron gain enthalpy decreases. Next, left to right, size decreases. You know that size decreases, tendency to accept electrons will be increased. Electron affinity should increase, but still there are some exceptions. I have a data over here. This is the exact data. Lithium, beryllium moving towards the neon. Neon is a noble gas. Just do not have any exception. They do not want any electron. If you don't want any electron, your electron gain enthalpy will be positive. I have already told you, if you want electron, the electron gain enthalpy is negative. You don't want, that will be positive, right? Okay. So when you're moving from left to right, your magnitude is getting increased. Your magnitude is getting increased. Your magnitude is getting increased. There are some exceptions present over here. Your magnitude is getting increased. That means that you want electron. You want to accept the electrons effectively. Just don't look at the exceptions over here, that I will discuss later. But right now, when you're moving from left to right, your negative electron gain enthalpy increases, your electron affinity increases. That means you want electron, because your size is getting decreased. You can easily accept the electrons, right? Now, for the second period elements, what is the order? Now see. As you can see, neon being the noble gas coming at the end. Why? Because it is having fully filled orbitals. If it is having fully filled orbitals, it does not want any electrons to accept. Okay? They have stable electronic configuration. Their electron gain enthalpy is always positive. Their electron affinity is very low. They are having very low electron affinity. That means they have very less tendency to accept the electrons. Okay. Now moving towards beryllium, then nitrogen, then lithium, and all these elements. Now what is happening? Before explaining this, I need to explain you one more thing. That is exceptions. Then only you will be able to understand this whole trend. Okay. What is the exception? First exception is second period element is having electron affinity less than third period. What do you mean by this statement? Let's say I have boron, then carbon, nitrogen, oxygen and fluorine. Boron, then aluminium, then silicon, then phosphorus, then sulfur, then chlorine. That means that all these elements have greater electron affinity. This is the order of the electron affinity. Exceptional trend this is. If you want to have the vertical view, I can show you the vertical view also. Boron, carbon, nitrogen, oxygen, fluorine, aluminium, silicon, phosphorus, sulfur, chlorine. You can have the view like this also. Why? Why these elements being smaller in size having the less electron affinity? Because these all elements are having empty 3D orbitals. They can accept electrons effectively. This is the reason, but you don't require to learn any reason, but you should know the trend which is followed over here. Okay, remember the trend over here. Group 1 has more electron affinity than group 2. See, if I talk about lithium and beryllium, है ना, electronic configuration 1s2, 2s1, electronic configuration 1s2, 2s1. This is the electronic configuration present over here, right? So lithium and beryllium, if I talk about the stability order, so beryllium is more stable than lithium, right? So if it is more stable, the removal of electron is hard. So always remember that electron affinity, of beryllium is greater than lithium. Always electron affinity of beryllium is greater than lithium. Okay, remember it very nicely, because you know that this is your group number 1 having the electronic configuration as ns1. This is group number 2 having electronic configuration as ns2. So already you know that ns2 is having stability of the fully filled s orbital, and it will require energy to accept electron into it. Now we talk about the group 14 and 15. Let's say I have group number 14. Let's say I have group number 15. If I talk about the general electronic configuration, ns2 np2. Here I have ns2 np3. Right? This is the electronic configuration. Okay. So if I make the p orbital diagram, over here, you can simply see that electronic configuration for the p is this, electronic configuration of the p is this. So which is stable? Obviously this is stable. Why? Because it is half filled. If it is half filled, it will be more stable. So acceptance of electron is more in the group number 14. You have to remember this. Electron affinity of group number 14 elements is greater than group number 15 elements. And just remember that nitrogen, phosphorus, arsenic, antimony and the bismuth. Nitrogen is having the positive electron gain enthalpy, and rest all of these elements are having negative electron gain enthalpy. That means that nitrogen does not want to accept electron, The reason is the same. It is having a very, very small size. The acceptance of electron requires very high energy because it is already stable, half filled p subshell, right? So remember this thing very, very nicely. That which all elements are having positive value of the electron gain enthalpy. Nitrogen, I have already told you. Alkaline earth metals, I need to tell you this thing also. I have told you that electron affinity of group, I should not write beryllium or lithium. I should write group number 2, then group number 1. Always, beta, always this is followed. Always it is followed. And even I should tell you one more thing, that alkaline earth metals, I should tell you one more very important thing, that alkaline earth metal having electronic configuration as ns2, which is very stable, have positive electron gain enthalpy. Their electron gain enthalpy is positive. That means they do not want to accept the electrons. So remember this thing very nicely. Okay. So nitrogen is having the positive electron gain enthalpy, alkaline earth metals and the inert gases. Inert gases is already stable. They are having ns2, np6. It is having ns2, and nitrogen is having smaller size and exactly half filled electronic configuration. But that does not mean that all of the group 15 elements are having the positive electron gain enthalpy. It is only valid for the nitrogen. Okay. Now, group having the highest electron affinity, which is the group? That is the group number 17. You know that why it is so? Because they are having electronic configuration as ns2 np5. After accepting one electrons, they become ns2 np6. They are becoming the noble gases, they are becoming the stable. So why they will not require the electron? They are just in one shot of an electron to get stabilized. Okay. After that we have group number 18. Group number 18 is having the lowest electron affinity because they are already stable. So why they will require an electron? Why? They don't need any electron. I have already told you they have some relationship with the god. Like they have some superiority, that they are always in the swag. They don't react with anyone. Okay. Elements having the highest electron affinity. See, group number 17 is having the highest electron affinity among all of the groups. In the group number 17, you have to know that fluorine, chlorine, bromine, iodine and astatine. So, there is an exception over here. Chlorine is having greater electron affinity than fluorine, and I have explained you this over here. I have written this thing over here. I have written this. So, you know the order, you know the answer. The answer will be chlorine. Elements having lowest electron affinity. Noble gases are having the lowest electron affinity. Noble gases are having lowest electron affinity, and they all have the positive electron gain enthalpies, that they don't want any electron, and in that neon is having the least tendency to accept electron. Neon does not want to accept electron. The whole of the periodic table, if there is an element which does not want electron, that will be the neon one. That will be the neon one. Okay? Just don't forget this. If you want to have the order, I can write the order also. See, the 15th order is phosphorus, arsenic, antimony, bismuth, and then nitrogen. Nitrogen is having an exception. For the 16th, sulfur, selenium, tellurium. If you want to have radioactive element, you can write, else it's not asked. Then will be oxygen. Okay? And for the 17, it is chlorine, then fluorine, then bromine, and then iodine. So exception is here. Do not forget these trends. Do not forget these trends. These trends are very, very important, 15, 16 and 17. Rest all exceptions I have discussed. So this is very, very important. Okay. Next we have a question over here. Correct order of the increasing electron affinity. Now you have to write the correct order of the increasing electron affinity. You know that in between sulfur and oxygen, sulfur is having. In between chlorine and fluorine, chlorine is having. So just pick up this order and put. And in between sulfur and chlorine, chlorine is having, because chlorine is present in the 17 and chlorine is the element which is having the maximum electron affinity in whole of the periodic table. So there is no exception, there is no question even. Okay. So chlorine first, then fluorine, then sulfur and then oxygen. So answer number first, option number first will be the answer. Okay. If you are confused, no, there will be no confusion. Everything is fine. Chlorine will be the highest one. There is very direct answer. I don't think so there will be any confusion. Every question is from the previous year. Every question is from the previous year. Which of the following process involves absorption of energy? See, accepting electron into the chlorine is an exothermic process. You know, I have told you that what all elements are having the positive electron gain enthalpy: alkaline earth metals, noble gases and the nitrogen. So rest all of the elements wants electron. So their electron gain enthalpy will be negative. Okay. So this process, this electron gain enthalpy is negative. So there is no requirement of energy to enter that electron into the chlorine. Okay. O2 negative is becoming O negative is becoming O2 negative. That is, you are adding an electron into the O negative to become O2 negative. That is something, there is a process. This process will require energy. It will require very high amount of energy. Already oxygen, then you formed O negative. Now you are forming O2 negative. Already that extra electron. Already this O negative. Already there is an extra electron. है ना? Already there is an extra electron which is creating inter-electronic repulsion. Already it is creating what? Inter-electronic repulsion. So if you are adding another electron, you have to supply energy, right? Here there is no problem. Okay. Okay, now something you need to understand. You are adding Na positive and then you are adding an electron. You are becoming stable. Neutral atom is always more stable than any of the charged atom. So this process will also be exothermic. You don't have to supply any energy. Only this process will be endothermic, and you have to tick this answer. Very, very important question. All the questions are from the previous year. Some of them have year written, some of them are not having year written, but all of them are previous year. Remember this. Which set of elements show positive electron gain enthalpy? Everybody knows this. Noble gases, alkaline earth metals and the nitrogen. Noble gases and the nitrogen, we have got our answer. Next. Which of the following is having the highest positive electron gain enthalpy? Highest positive. Don't want any electron. Not at all want any electron. Highest positive electron gain enthalpy. I don't want any electron. Highest positive. I just don't want to see the face of the electron. What is the answer? O negative. Fluorine is neutral. Positively charged will have to want electrons because they are in the shortage of electrons. So they require electron. So O negative, anion. It does not want any electron. Next we have the formation of the oxide ion required first and exothermic then endothermic steps as followed. Why? We know this. I don't think so that we need to see the options. What they are saying first you are adding an electron, that process is exothermic. Then you are adding the another electron, the process is endothermic. Why it is happening so? You know that extra electron already creating the inter-electronic repulsions. O negative ion has comparatively larger size. There is no reason of the size. Oxygen has a high electron affinity, that is fine. But this is not the answer. O negative ion will tend to resist the addition of another electron because of inter-electronic repulsion. Because of inter-electronic repulsion. So answer will be option number 3. Oxygen is more electronegative. That does not indicate the reason of this answer. What is the value of electron gain enthalpy of sodium positive if its ionization enthalpy is this? Very easy. You have sodium. Just remove one electron, form Na positive gaseous plus electron. This process will require some energy equal to plus 5.1 electron volt. And if you want to add electron into this, you will see that same amount of energy will be released. So what they are saying, electron gain enthalpy value of Na positive, you have to calculate if ionization enthalpy is 5.1 electron volt. You are removing electron from sodium. Now you want to add the same electron, you have to supply the same amount of energy. I have already told you in the notes, previous year question. So the answer will be minus 5.1 electron volt. Answer will be minus 5.1 electron volt. Now we are moving towards the next property, which is called as electronegativity. Now what is electronegativity? Electronegativity is a tendency of an atom to attract shared pair of electrons towards itself. Let's say I have a bond between A and B. There is a A atom, it is having its electron shared with the B atom. Let's say with the help of some measures like Pauling scale, Mulliken scale, I have calculated the values of both of the atoms A and B. And I know that the symbol of electronegativity is this guy. Remember this, okay? You have that electronegativity of A is greater than electronegativity of B. You know this thing. So what is the result of this respective difference in the electronegativity? It means that the electron will be shared towards A more because A is more electronegative. It is having more tendency to attract this shared pair of electron towards itself. Okay. As a result, it will form A as del negative and B as del positive. See, the meaning of this del negative and del positive, what do you mean by these del negative? This del represents slight charges. This del represents slight charges. There is a slight charge which is created due to the difference in the electronegativities. But if you break this, you will get A negative plus B positive. Electronegativity is required because when you break the bond, you are not knowing where to keep the negative charge, where to keep the positive charge, specifically in the organic chemistry. So wherever there is a shifted electron pair, which atom is shifting electron pair towards itself will be more electronegative atom, will be having the negative charge. Or whenever you break the bond of OH, why do you write O negative and H positive? You like, acha lagta. That is not the reason. Na? You have the electronegativity of oxygen as more. So this is the reason. Okay. Whenever you are writing del negative and del positive, you have to understand that one is more electronegative and other is the lesser. You know all these things. Okay. Now, valid for the combined state. Always electronegativity is valid for the combined state, because we never talk about the individual atoms. For example, I say I have a molecule which is OF2 and one is OH2. है ना? If I make the bond of OF2 and in other I make the bond for the OH2, what you will write? In one of the case, oxygen is having del positive, and in other case it is having as del negative. So I cannot say that oxygen is always electronegative. I cannot say oxygen is always electronegative. We talk these things in terms of the compounds present. In some compounds it might be more electronegative, in some compounds it might be less electronegative. So we talk in the combined state for the electronegativity. Okay, unitless and dimensionless, it is not having any unit or it is not having any dimensions. Okay, inversely proportional to the radius, very true. If you have a bigger size, why you will accept electrons? Why you will have a tendency to attract that electron? What does that mean? You have a bigger size, you have a smaller size. This is your nucleus, this is your nucleus. Now this is electron, this is electron. What is the distance? Here the distance is more, here the distance is less. So it can attract this electron more effectively. It will require some different measures to accept this electron. So understand that smaller the size, greater is the electronegativity. Radius more, electronegativity less. Greater the size, less is the tendency to attract the shared pair of electron towards itself, because the distance between the nucleus and that electron will increase, the hold will be decreased. Okay, directly proportional to the effective nuclear charge, very true. You know that Z effective increases, है ना? Your size decreases, your electronegativity increase. You can simply have a case like this. Just remember this formula and reach to your answers. Smaller size, more the tendency you have to attract that electrons, and that is related to the Z effective, like this. Next, now I have written two scales over here. That is, one is the Mulliken scale and one is the Pauling scale. You just have to remember these formulae. You just have to remember this respective formulae. Nothing else. It's not asked. It's never asked, but you should know how you calculate the electronegativity with the help of the Mulliken scale, or how you calculate with the help of the Pauling scale. That is much required, but not after that. Okay. So if you want to know the terms, one is your ionization enthalpy, one is your electron affinity. Just have the two sum divided by the 2, you will get the electronegativity of the respective atom. Okay, always these two values will be taken in the electron volt unit. If you have the mole unit, you have to convert that into the electron volt, then only you will be able to calculate the answer. Okay, here you have the difference of electronegativities. Here you have a delta E. You can calculate the delta E with the help of this respective formula, which is related with the bond energy. Again, I am saying that not any question is asked on these two scales, but you should know the data. Okay. Next, this is important. This is asked. Okay. First of all, directly proportional to the oxidation state. Now, what does that mean? I should not say oxidation state. I should say the positive oxidation state, because let's say I have an atom, I have an ion Fe plus 2, and then I have an ion Fe plus 3. I have these two kinds of ion. So which is having the greater electronegativity? Because size is the main role. Fe plus 2 is having greater size as Fe plus 3. And you know that electronegativity is inversely proportional to the size. Greater the size, greater is the greater the size, less is the electronegativity. Just see the charges. Greater the positive charge, less is the size, more is the electronegativity. Greater the positive charge, more is the electronegativity. Greater the positive charge, less is the size, and relate these two, and you will get your answer, right? Directly proportional to the percentage S character. Very, very important. You have your hybridization as Sp, then Sp2, then Sp3. Percentage S character. Here you have 50%, here you have 33.3%, and here you have 25%. More is the percentage S character, more is the electronegativity. This is required In so many questions in the chapter chemical bonding, we need to learn every of this. So it is important to memorize this respective factor. More percentage S character means you are more nearer to the nucleus. You are like very near to the nucleus, and if you are very near to the nucleus, you have tendency to attract electrons very effectively. So you can have this point related to this explanation. Okay, perfect. Values of electronegativity. Phone call. Phone call. Just learn phone call. Okay. Fluorine highest, cesium lowest. Remember, you know that there is a compound known as cesium fluoride. This compound is having maximum ionic character. If there is any compound possible which is having the maximum ionic character, is cesium fluoride, because one is highly electronegative, other is highly electropositive, and they are having maximum electronegativity difference, and greater the electronegativity difference, greater is the ionic character. We know all these things that we will discuss in the chemical bonding also. Group 1 lowest, electronegativity lowest, group 17 highest, and group 18 0. We don't attract any electrons, so we have zero electronegativities. Okay, learn these things very nicely. Electronegativity of the following elements increases in the order. Phone call. So nitrogen will be the highest. I don't think so that we have to use any brain in this question. This is already very easy. They give so easy question in the NEET examination. I don't have to use even 1 second. See, this much scoring your inorganic chemistry is. This much scoring. I have already done all these things. Diagonal relationship. There are elements which are having diagonal relationship. Lithium is having properties similar to magnesium, beryllium similar to aluminium, and somehow boron is having similar properties to silicon. Why? Why the elements are having diagonal relationship? Why they have similar properties? Just one reason. They have similar charge by radius ratio. They have similar charge by radius ratio. Lithium, if I talk about lithium having the charge +1, if I have magnesium +2 charge, and they have some radius over here. They have some radius over here. So if I see this respective charge by radius ratio will be almost similar. Almost similar. Okay, so remember this thing, similar charge by radius ratio. Just click this option. Why there is a diagonal relationship between elements? Because they have similar charge by radius ratio. That's it. Okay, first member of every group. You study the chapter P block elements, and even the S block elements. Always you study the statement that first element is having very different properties from other of the elements. Why so? Now the reasons. Always it will have the smaller size, because top to bottom size increases, so the first element will have the small size. Next, large charge by radius ratio. They have a very smaller size, they have a charge more, है ना? Okay, I can say that charge will be same for all of the group elements, but the smaller the denominator, more will be the whole number. Like if I say I have lithium, sodium, potassium, everybody will have the +1, +1, +1 charge. But hypothetically, I can take radius as 2, 3, 4, right? Obviously, size is increasing, so I can hypothetically take these numbers. So you know that the highest value will be for this, na? Because it is having the lowest denominator. The lowest the denominator, greater is the whole number, right? So electronegativity is high. They have a very high electronegativity, and even their ionization enthalpy is also very high. These all factors tells you that the first element is having very different properties from the other elements. So whenever you see this question, there will be the 4 points that can be asked, and you have to see all these 4 points, nothing else. Next. The diagonal relationship is due to the similar polarizing power. Yes, you need to remember this also, that this charge by radius ratio is also called as, polarizing power. Do not get confused with this word. This is nothing, just charge by radius ratio, nothing else. Okay. After this, oxides. There are many number of oxides present. Basic oxides. Who form basic oxides? Metals. Like group 1 and 2, all elements. Left to right, basic character decreases, acidic character increases, because left hand side you are not, you are metal form basic oxides, right hand side you have non-metals, they form acidic oxides, so the character decreases accordingly. Top to bottom basic character increases. Okay, when you're moving from top to bottom, the basic character increases. Acidic oxides formed by the non-metals, when you're moving from left to right, acidic character increases, top to bottom it is decreased. These are the trends you need to remember very nicely. These are the trends you need to remember: basic oxide, acidic oxide. Now why do we call it as a basic oxide? Like I say, I have sodium, I dissolve that into water, so I will form a base. Similarly, I have, you can take its oxide also, Na2O, simply take the oxide. If I take sulfur oxide, I dissolve that into water, I will form H2SO3, and that is an acid. So non-metal always form acidic oxide and the metals always form basic oxide, because when their oxides are dissolved in water, they form base or the acids. If they form base, they are called as basic oxides. If they are forming acid, they are called as acidic oxides, right? Now, neutral oxides are also present. You have to just remember the which all neutral oxides are present. They don't behave like either acidic or basic, but it is asked that which all elements or which of the compounds are neutral. Question has came. Okay. Amphoteric oxide. All these elements form the amphoteric oxide. Remember all of them: zinc, aluminium, lead, beryllium, tin, antimony, arsenic, gallium, chromium. Everybody forms the amphoteric oxide. You need to remember all of these elements. Don't forget. Everybody is forming the amphoteric oxide. Everybody is forming zinc, aluminium, lead, all of these elements. So I hope you will remember this. And amphoteric oxides question is always asked. It's very, very important. Now match. You have to match now. N2O. N2O is neutral, so A will have the option as fourth. Barium is a metal, so it will form the acidic basic oxide. Arsenic is amphoteric, and chlorine is acidic. So option number what? A is fourth. In what options? B and C. B is first. Okay. C is second. So this is the answer. Very easy. I know all the oxides. I can, in just 2 seconds, I have answered the question. We have answered the question. So this much is the power of the inorganic chemistry. Okay. Which of the following oxide is expected to react readily with NaOH? See, NaOH is a base, so it will react with an acidic oxide or the element which can form the acidic oxide. This is basic, this is basic, this is neutral. So answer will be Cl2O7. And we have done the whole revision in the one short lecture. I have included everything. In this respective one short lecture. Just go through it, just study hard from it, and just do the bale after this. Okay. And periodicity is very important. It is having use in so many other chapters that you will study, that we will study afterwards. Okay. So revise very nicely, solve how many number of questions you can solve, maximum number of questions you can solve for whatever respective examinations you are following. This will be followed for the both NEET and JEE. If you're doing for the JEE, it's enough. If you're doing for the NEET, it's okay if you're learning some 1 or 2 extra things. That is not a problem. You should not have any less number of data available to you. You should have the apt data available to you. Okay. So thank you so much for attending. Thank you all. PW English Wallah, Channel V, you all students. Love you so much.